Again, just like yesterday, if anyone has an issue with YouTube at some point, especially the speakers, let me know and we can like pause the stream. Though it didn't really seem to be an issue yesterday. Okay, I think we're ready to start. It's close enough to what I was hoping in terms of people turning up. So yeah, I hope you're all ready to see some interesting things with what's going to happen, how operations have been going and, what's going to happen with phase 3. And then in the afternoon, we've got some interesting things relating, pulsars and transients and VCS. I'm happy to talk to you guys while I'm still awake. At the moment, it's only 8 p.m., but it's going to get quite late by the end of it. Anyway, Randall, are you ready? Cool.
Yeah, no worries. Thanks, Luke. Good day, everyone. Welcome to the second day. So we've got technical talks this morning, and we're going to start out with Greg Sleep, who's going to tell us about the MWA data lifecycle. So take it away, Greg, if you're ready to share your screen.
Cool. Yep. Doing that and do that. And we'll do that. All right. Okay, I think we're ready to go. Right, hang on a sec. Oops, sorry about that. Mia, what's the deal with this being so small? Sorry, I'm just having a bit of a...
Okay, you can make that.
Sorry. Right, there we go, PowerPoint fail. Okay, cool. Good morning, everyone. So my name's Greg Sleep, and I'm the MWA data manager. And today I'm just going to be, or this evening, depending on your time zone, I'm going to be talking to you about the MWA archive and a bit of an update on that, and our data lifecycle policy update, and also just about what's happening with the MWA SVO and a few other things going on in the world of MWA data. So this pretty much sums up most of my talk, is data everywhere. So this is the current state of the archive and the growth that we've had over the last sort of 6 or 7 years since commissioning. So the main thing to see here is that we are fast approaching 35 petabytes, and our allocation at Pawsey is 40 petabytes. So you can see that at some point we're going to hit a bit of a wall, which I'll talk a bit about later. This plot as well shows the data growth, but it's already had any deleted data removed. So where people have asked me to remove data for them, this does not count on this plot. So basically, this is what we actually have in the archive right now. If we included the stuff that has been deleted, then we would have actually been way off the scale here with about an extra 9 petabytes. We're going to use the mouse. So this is a bit of a summary of the usage by each project. So this is as of right now. So you can see the interesting thing actually here is to see that the other part of the pie chart is getting bigger and bigger each time I show this plot. And it really just goes to show that a big chunk of our archive is actually full of lots and lots of small to medium projects. And so they're now taking up a good quarter, more than a quarter of the archive. Gleam is the next biggest taker with 11%. And then you've basically got some VCS stuff, so FRBs with the MWA, solar, some parks and ASCAP shadowing, which should actually end up sort of mostly going to zero over time as observations are checked. And the G0057 MWA Pulsar survey, which is the smart survey. The usage by the VCS team is a little bit tricky in the sense that it looks like they're taking up a lot of space, and they are, but a lot of that space can be reclaimed once they've checked their data, because there's a bit of a recombine process that creates redundant data that can then later on be removed. So the actual usage is a bit smaller than that. So now the next section of the talk is just to talk about what we do with the fact that we've actually got all this data. So this plot here just shows the next few months, and the big red line there is our limit at Pawsey, which is 40 petabytes. There's no hope in sight for Pawsey to give us a reprieve and extend our capacity in the short term and possibly even the medium term. The next time we're going to see an increase to our archive is probably with the $70 million Pawsey refresh, but that probably won't be for another 2 years or so, and we don't have many details about what that will look like yet. So as you can see at the moment, we're in July, and all things being equal, assuming that no one asks me to delete any data for them, we're probably going to hit the wall in about January or February. And you see the different colors there just relate to the different configurations of the telescope. So in the extended or long baseline configuration, we actually grow at a higher rate than in the compact configuration. So having October, November and December in the compact config will actually slow down our race towards the brick wall. So this is how the MWA life cycle or data life cycle has been so far. As you can see, we go schedule, observe. The data sits in the archive during the 18-month proprietary period, where it's only accessible by the PIs and the MWA members. And then after that, the data becomes public. And that's pretty much where the life cycle has ended for the MWA up until this point. So you can see that's not really a sustainable approach. So we need to actually fill in the missing box there, which is to actually have a formal process codified in policy for data removal. So an archive policy team was formed earlier this year, led by the principal scientist and having representatives from all the science groups and the operations team. So a recommendations document was submitted to the MWA director. Melanie then reviewed that and then put that document to the board. The board is discussing the ins and outs of that policy at the moment. However, I thought I'd still present to you the main gist of that policy, even though it may end up possibly changing, but possibly not. So the idea is that the MWA will continue as a raw data archive. It's always been that way, and it will continue to be that way. The archive will operate as a FIFO queue, so first in, first out. So new data will come in, and the oldest data will be removed just in time to make sure that we've got room for new observations. And the data will always be guaranteed available for the proprietary period at an absolute minimum. And so far, that's not been a problem since we've been operating for 7 years or so. And so we still have data dating back to 2011, 2012, 2013. So I don't see that being a big issue. So one way that this may work, and the details are still to be fully fleshed out, but the main idea would be that we'd have some sort of monthly delete cycle. There would be a list of what we need to delete in order to make enough room for new data made prior to that delete cycle. So say if the deletes happened at the beginning of the month, perhaps 2 or 3 weeks prior to that, we would provide the collaboration with a list of observations that would be deleted in the next cycle. So PIs are able to apply to the MWA director to hold specific data sets if they believe that there is a justification as to why they shouldn't be deleted. This would only be for 12 months though, so it buys you some time. But it must be pointed out that the amount of space that we would have reserved for this sort of held data is only 15% of the archive. So most of the archive will be the first in, first out queue. So what can you do? So in the meantime, it's probably a good idea for us to all focus on identifying any unneeded and bad quality data. So this, I guess, is data that is of no use to anyone. I do realize that there are cases where science data is maybe not useful for one science case, but may be useful to another. But I would be sure that there is data out there that is probably just of no use to anyone, and that's the stuff we should get rid of first. Any old data that we can identify this way can be deleted at any time by myself or the ops team. And this buys us valuable time where we don't need to actually engage in the monthly delete. So as part of this, I aim to provide a lot more information to PIs for how much their project is using and whereabouts in time their data is, so that they've got a better idea on exactly what's coming up in the delete cycle once it happens. There will be a formal process or application process to apply for holding some data. And just as an FYI, with people coming to me and asking me to delete data for them as PIs, we've removed about 9 petabytes or so. So without people actually proactively doing that and letting me know, we would have already hit our wall several months ago. So, the EOR team actually and the VCS team have been quite proactive in that. So thank you for that. All right, on to the ASVO update. So the best news is that we actually have our new starter, Harry Barlow, who Melanie introduced yesterday in her talk. Harry's an experienced software developer, so he actually is a bit of a powerhouse to add to the team to actually get a lot of stuff done for the ASVO. So the first thing he worked on was our MWA Data Central single sign-on. So this basically means that you can log into Data Central with your MWA account, or you can log into the MWA with your Data Central account. He also did a lot of updates to the backend for security and stability, set up a better test environment, and intends to produce a lot more smaller but more frequent releases to the ASVO. So he's worked on modern refreshed front end using React.js, which will be released sometime this quarter. And also has been working on building a new search interface, which will replace the old Django one. And this is a sneak peek as to what that looks like. It's pretty cool. Lots of search things on the left-hand side. So I'm sure you'll all see this very soon. So we've also been working on an improved tap service. So if you don't know what a tap service is, it's basically a metadata service you can access over the web using certain client tools like Topcat or PyVO in Python. And it basically means you can query MWA metadata directly that way without needing access directly to a Postgres database or anything like that. So we've improved support for the standard OBSCore features and also added some MWA specific metadata as well, which will be very handy. So this is a quick update on our ASVO stats. Probably the interesting thing to point out there is that 2% of the ASVO jobs are from the public, with only 1% of the data served out. But this is a bit misleading. So members of the public, so non-MWA members, generally won't download the raw data. So the amount of data they're downloading is a lot less because they're using the averaged sort of cotted data rather than the raw data. But the members of the public actually account for 61% of our registered users and 47% of our active users. So hopefully we'll see over time the number of, I guess, publications by members of the public and non-MWA members increasing as they start to use the ASVO more. This is just a quick plot just showing the growth or how much users have downloaded over time. I won't spend too much time on that because I think I'm running out. So future work, yeah, never set it to 2020. Let's just skip that year. But the future work is exciting. So we basically have Garawala coming online soon. Melanie talked about this yesterday. So it's the Wadri name for Spider. It's dedicated for use by the MWA collaboration. You can see the nodes are quite powerful. It can do native or container workloads, which is really handy, especially for software that's tricky to compile using containers. We're in an early adopter phase at the moment, and the time allocation policy to apply to get access to Garawala is being worked on at the moment, and you'll hear from Melanie about that over the next few weeks. So we also scheduled to get some new MWA ASVO processor nodes at Pawsey. We've been waiting quite a long time for them, and hopefully they'll be available soon, and that should allow us to get through the queue a lot quicker. We also have a backload of ASVO requests that Harry will be dedicated to, so you should be able to smash a lot of these things out quite quickly. And we've also been working on the new Correlator data capture, flow, and testing and benchmarking. New ingest servers at Pawsey as well as part of that, and also working on realigning the data flow to use the 100 gig links instead of the 10 gig link that we've got at the moment. So this is what our current data flow looks like. So the main area that we're working on as part of the new Correlator project will be to actually replace these sections here. So I don't know if you can see my mouse, you can't, but the Correlator online archive and then the link to Pawsey. So in the phase 3 world, this is basically the end of phase 3. So this is the phase 3 with a capital P. You'll notice we've got a new 100 gig link, well not new, it's an existing 100 gig link that takes data from the Correlator to a data cache that's down at the Curtin data center. And then data will then flow from there over 100 gig link over to Pawsey. And so by the end of phase 3, we would actually have quite a few more ingest servers at Pawsey as well, because they'll be needed. But Brian will talk to you more about phase 3 in general. Sorry, not phase 3, the MWAX Correlator in general. So I'll skip that. Last thing I want to mention is that we're working with Pawsey on a joint project to evaluate Ruscio. Ruscio is a scientific data management platform. It's open source and developed and used at CERN. So the Atlas experiment has over 450 petabytes managed through Ruscio, and it may provide more flexible ways for us to replicate and move data. So for example, to transfer it to other institutions that are MWA members, but also within Pawsey and also from the MRO to Pawsey as well. It's policy driven or interactive. So it's actually got an interface that can be used to move data around. So we're basically setting up a demo, testing it with MWA data, but we're really just in an exploratory requirements phase just to see if it actually has merit and has benefit for us to implement. The AENAS project in Europe evaluated Ruscio for SKA last year, and they were actually quite positive about it. So we're digging into that report to sort of see any sort of challenges or pitfalls that they saw. The quick executive summary was that there were a few little things, but they're all things that are meant to be fixed in 2020. And that's it for me. So thanks for your time, and yeah, let me know if you've got any questions.
Thanks very much, Greg. I saw Miguel was very polite and put his hand up first, so why don't you go first, Miguel?
Okay, so a very nice presentation, Greg. And so I think this is more of a comment and less to you than to the board and management of the MWA, is that I think this idea of first in, first out, and a one size fits all for all data with a time really makes no sense. And it's really shoehorning a policy. And so part of that is, for example, Brian mentioned, the EOR collaboration. Kath has been very aggressive on trying to reduce our data load. That being said, our most valuable data, all of the work that Kath talked about yesterday involved data from 2013 and 2014. And because the RFI environment's getting worse, that's actually some of the historically most valuable data that the EOR team has. And so I think the project would be well served to look at different users and different cases and talk about keeping data based on value, not based on, oh, it's so many years old, thus it must have no value. So anyway, again, that's not for you, Greg. This is more of a comment to the wider scheme that the policy, I hope the board is discussing this and stuff like that. That policy just really seems like the project shooting itself in the foot. So anyway, that's just a comment. I don't know if anybody, if you just wanted to respond to that, but that was just a comment I wanted to throw out there.
Sure, yeah, thanks for that. I might just pass you over to Melanie. She might be able to explain from the management point of view.
Can you hear me, Miguel?
Yes.
Yeah, so there's two components to this policy. So there's the chunk of the archive, which will be, as Greg said, which is a standard first in, first out component of the archive. And then there is a reserved part where what we've termed data working groups, but are basically science working groups, can nominate to store data for longer periods of time. So each data working group or science working group will be able to nominate which data sets they want to keep for longer periods out of the FIFO queue. So we're not just having data drop off based on the date. The science working groups do have the opportunity to mark data as valuable and to keep that for a longer period of time. That said, do you want to respond to that?
Well, but the presentation that you said, the presentation stated that that was for 12 months and 15% of the total storage.
That's
and again,
correct.
that felt.
Yes.
And that just seems very short. That's what I'm responding to.
Okay. Well,
I'm not responding that there's a process. The idea that this is a 12-month grace period and only 15% means that you have put in a policy in place that means that the most valuable EOR science will be thrown away in a year.
no, the policy actually allows you to request another extension on every 12 months. So that probably wasn't clear from the presentation, but that is actually in the document. So if the EOR team deem that the 2013 EOR dataset needs to be kept in their allocation in perpetuity, you can do that. It's just you have to request it every year, because we don't want things to just fill up in the dedicated piece and not give us a piece of the FIFO queue to be able to continue to observe and collect new data. Now, the other thing is, hang on, I have to finish. The other thing is that, we've long had this discussion about the distinction between the MWA Observatory as a facility that collects data and the MWA collaboration, which is the group of people that utilize those data. As Greg said in his presentation, with respect to the data lifecycle, we've not ever been in a position before where we've had to worry about that. And so we have had the luxury of being provided with a storage mechanism that's allowed us to keep data from the start of the observation period. We don't have that anymore. That's just a fact. So there's two things that you can do to alleviate this. So if you're a science team member, you can either find more money for the MWA to pay for more long-term storage archives, which you can keep your data in for longer, so through your national MWA consortia, or you can move it and keep it somewhere locally yourself, and we're giving people time to be able to do that. But this is the reality, is that we've got 40 petabytes and we have a machine which is collecting of the order of a petabyte of data a month, and we've been operating for 7 years. So we can't keep everything in perpetuity. We have to have a mechanism to deal with that. And of course, we're happy to understand that some data sets are more valuable than others, Miguel, but this has obviously got to be balanced across the entire collaboration.
So Melanie, just to say this, I am trying to ask that the value be balanced across the collaboration. That is the request. And I think part of the thing that is tricky is I agree with you about money. But the flip side is that if you ask, for example, the EOR collaboration, who has already halved their data volume in the last year, something like that. But if you ask us that we need to go do it ourselves, that's fine. But that means that we can bring less money to the project.
Okay, folks, we have
so
to
there's a
move
real
on.
cost. So anyway, I will let other people talk, but I'm just going to raise my hand that I think that this is something the board should think hard about.
Okay, thanks guys. I'm sorry, Divya and Shinoa. Divya had a question and Shinoa had a question in the chat. So perhaps, Greg, if you can, or Melanie, can you answer that offline? That'd be great. Hopefully Mia has set up in the background. Perfect, excellent. Next talk is Mia Walker talking about phase 3. Go ahead.
Hi, can everyone hear me? All right, so thanks for joining. My name's Mia and I'm the program manager for the MWA, and I hope I've met most of you. If not, the short version is that I work at Curtin. My background is in electronics engineering, and I have 2 cats who like interrupting my telecon, so it's a really good thing I'm not working from home today. So this talk is about the vision that we have in the operations team for the next phase of the MWA telescope. Phase 3 involves some really significant upgrades, and it's planned to take place over 5 years, from 2021 to 2026. I'm going to talk about the upgrades that we have planned and how it's possible to implement them. And all of the work that we want to do depends on input from you guys, so from our collaborators and our scientists and what you need in a telescope. So after my talk, we have Brian going into more detail about the new correlator, and then we have a full hour of discussion of phase 3 led by our director, and we'd love to hear your thoughts. So as you know, I think Greg just showed this slide, the MWA is made up of antenna tiles that are spread across several kilometres, and the tiles send radio signals to receivers for initial processing, which is then cut up into fine channels and transferred to the correlator. Okay, you can see that. Then the visibility and the raw voltage data is streamed 700 kilometres to Perth and stored at the Pawsey Supercomputing Centre. And then astronomers access the data archive through the All Sky Virtual Observatory, or ASVO. Right now, there's a total of 256 tiles on site, but our current correlator can only handle data from 128 tiles at once. So every observing semester, we reconfigure the array between the 2 different sets of antennas, which are called the compact and the extended configurations. And the operations team is working on enhancing the entire signal path for phase 3 of the telescope. And this is going to allow us to, or all 256 tiles to be included in the array at once. This is going to give the MWA higher sensitivity, spatial resolution, and UV coverage. This benefits each of the MWA science goals, and it's going to reinforce its place as a leading precursor instrument for the SK. So this is what the new signal path is going to look like. I'm not going to make you play spot the difference with the old diagram. I'm just going to point out the changes and explain what each of them mean in a bit more detail in the next slides. So we're going to have twice the number of connected antennas. We might upgrade the links between the tiles and the receivers. We're going to need new receiver packages and more of them. We may have to add media conversion servers. Of course, we need a new and improved correlator. There's going to be an increase in data rates out of the correlator. There's this new data cache at Curtin and more ingest servers at Pawsey and a larger archive size. So I'm going to go through the new signal path, starting with our dipoles, because it's the easiest. We already have 256 tiles on site already. So there's no need to install any more antennas for once, which is great news. But because there's more tiles, we'll be spending a bit more time doing maintenance, but we won't have to do any expensive reconfiguration trips once we're operating at full 256T. And we're already upgrading all the beamformers in the array to deal with obsolescence, but we may need to do additional development work if we're converting more tiles to fibre cable. What I mean by that is in the extended configuration, we have 56 of these long baseline tiles, which are up to 3 kilometres from the core. And instead of using these copper coax cable to connect them to the receivers, they use radio frequency over fiber, or RFOF technology. This is because we can't effectively send power and signal over kilometres of cable. So each of these tiles is connected to this beamformer interface, or BFIF, that provides the fibre and the beamformer power via a solar panel and battery system. So a really good upgrade option is to retrofit all the other 200 coax tiles with these fibre links. And a study still needs to be done, but using the fibre might have the benefit of getting rid of bandpass ripple due to long coax cables, which is, as I hear, a major issue for the EOR project. It would also simplify the signal chain if we didn't have some tiles on coax cable and some tiles on fibre. Depending on the number of new receivers that we get and their specs, there are different ways that we can implement this, which could potentially include smart boxes from SKA prototypes, modifying beamformers, and developing new power supply units on the old receiver pads. We will probably have to develop new power supply units for the beamformers anyway if we move the receivers to a central location. Which leads me to receivers, which are perhaps the trickiest part of phase 3. So as you know, we only have 16 of these receivers at the moment, just enough to process 128 tiles of data. When we're reconfiguring the array, we have to physically move these receivers to different locations to connect them with different tiles, and it is not a small job, and we don't have any spares. So when one receiver goes down, we lose 8 tiles worth of data immediately until we can fix it. And this is all custom hardware that has been running for almost a decade, and our operations team was not involved in the design process. So trying to troubleshoot problems can be a nightmare, as Dave Emmerich would tell you. So you can see why we're really keen to replace these receivers, but they're an expensive piece of kit. So without partner contributions, we may be forced to keep these ones in the field for phase 3. We are planning for that eventuality, but the best thing for everyone would be to completely replace them. Doing that would let us fix some of the problems with the current receivers, like we could oversample to get rid of the coarse channel bandpass edges that are a problem for EOR. Otherwise, we might have to live with having a hybrid system that's behaving like the old one, which doesn't have forward compatibility. But any new hardware is a win here. And by developing the firmware in-house or with a lot of involvement by us in the ops team, it'll be really easy for us to maintain and update the new receivers going into the future. We've done a lot of development work with FPGA and control hardware by National Instruments and with Casper snapboards, but we're looking at other options as well to cut down on cost without compromising on functionality. So we've partnered with our Chinese collaborators from Xiao this year to prototype a system based on hardware that they're pretty familiar with for VLBI, and that's looking extremely promising already. Other options are still possible if necessary, including a PXI system from Abaco and the Blue Ring RF system on a chip system being developed by CSIRO. We should know that the receiver doesn't just digitize, there's an analog signal conditioning component that would also need to be developed for phase 3 and potentially be compatible with both copper and fibre cables. Depending on the number of new receivers we get, we're looking at housing them all together in a nice central shielded enclosure, like the one that the SKA currently has on site. And of course, anything new that we put on site has to pass the observatory's strict EMC test limits. So if we can't get 256 tiles worth of new receivers and we have both new and old receivers running together on site, we're going to need to standardize that data stream before we give it to the new correlator. So this means having consistent sampling rates and packet formats and channel bandwidth to make everything compatible with each other. And this is a task of the media converter or MEDCON servers. To do this, or to get these servers, we propose reusing some of the 16 existing VCS servers. But if we get enough new receivers, we might not need these MEDCON servers at all, which is ideal because then we won't be adding extra unnecessary bits in the signal chain. This would mean the new receivers have to do the tricky corner turn operation, which is when packets are addressed based on their channel frequency rather than the receiver that they came from. And of course, our new MWAX correlator underpins all the phase 3 work to date. Brian's going to talk about this in detail, so I'll just say that we need a new correlator because the old one is both very old and has a hard design limit of 128 tiles and 30.72 megahertz of bandwidth. The replacement also has an FX architecture based on CUDA and developed on Cisco machines with NVIDIA RTX 2080 GPU cards. Apart from being able to correlate 256 tiles, MWAX has 20 times more options for frequency and time resolution. It uses industry standard hardware and software wherever possible, and it works on a multicast system. So you can have multiple users tapping into the voltage data at any one time. And most of the work needed to develop MWAX is complete, and we'll hopefully find out in the next couple of months if we were successful in our funding application to go ahead and purchase the hardware. Now, because of all the extra data we expect from having twice as many tiles in the new correlator, phase 3 called for a bigger data pipeline than the 10 gig NBN link that currently exists between the observatory and Pawsey. So we've installed a 100 gig link between the MRO and Curtin with these Cisco 9K switches at each end. So the MWAX servers send both visibility and multicast voltage data over the new link to one of 8 cache servers at the data center. Each of these servers runs an instance of NGAS, which is an archiving software package that we already use in the MWA, to store data temporarily in 2.5 petabytes of space. It's worth saying that if we had an even bigger pipeline, such as 300 gig, we'd be able to transmit all voltage data or increase the amount of bandwidth that we can process with new receivers. This would also let us have the correlator offsite, closer to where we do operations here at Curtin, which means easier maintenance and freeing up rack space in the control building. The last part in the new signal chain is the archive. So all data will be forwarded from the cache servers at Curtin to Pawsey, where it's stored on disk and tape and accessed via the ASVO, much like how it is right now. Because the input data rate and the archive size are going to grow, we have 2 more front-end servers ready for installation at Pawsey. And we're also putting in place a data lifecycle policy that Greg just talked about to manage our long-term data storage. Yes, so the MWA's allocation of the archive is currently 40 petabytes and it's almost full. So to realize the new capabilities of the telescope in phase 3, we're going to need a bigger archive. At the moment, we're investigating the use of Ruscio, which is a data management platform, which could simplify storage and access to some of our data in a split system with Pawsey. So that's a possibility, and perhaps an avenue for partner contribution in phase 3. When it comes to implementing all of these changes, there's a few different paths that we could take dependent on funding. A large part of the new signal path is already set in stone. So for example, the new MWAX correlator is common and a requirement to all of these paths. So we can't do much else until that has been put in place. We still haven't heard back about our funding proposal yet, but this is on the critical path. And as I foreshadowed earlier, the biggest difference to how we implement phase 3, how long it takes, the risk involved, and the quality of the data depends mostly on the number and the type of new receivers that we can develop. What we want to do ideally is develop an entire suite of 16 new receivers alongside the existing phase 2, then switch over to them and complete the rest of the upgrade with 32 new receivers in total. That would be the best outcome, though it has the highest upfront cost. A route that could be much more expensive and risky in the long term is having to use our legacy receivers in the array at the same time as our new receivers operating in a compatibility mode and routing data through the media conversion servers that I talked about. This is still possible though, and we recognise that funding opportunities and timelines may not be able to support the ideal case, and this might be the most realistic way forward to achieving phase 3. Also included in this diagram is potential upgrades of fibre cabling to all tiles, increasing the size of the data link to Pawsey and moving the correlator offsite. Lastly, this is the expected timeline for the MWA. So by the end of this year, we hope to have selected a receiver candidate and finished work on the MWAX correlator. And by the middle of next year, we'll have finished prototyping the receiver as phase 3 officially begins, which is a 5-year period starting from July 2021. Then we purchase and install the hardware, deploying it on site and making other changes needed to the array, such as rolling out more fibre. And we complete all this before the end of 2022, so that there are a full 3.5 years of observations with the new system, however that looks. And after phase 3 is complete, the ASVO node will still be supported for 18 months while astronomers have proprietary observations. So for reference, the SKLO is expected to start full array construction in April 2024 and complete that in 2028. So we have the ideas and we have the know-how to make phase 3 happen, but the implementation path is going to primarily be determined by the number and the nature of funding streams that are established with our collaboration partners, both in-kind and cash contributions. And of course, we'd love to see our current partners return for phase 3 membership, and we really welcome new members as well. And any questions or expressions of interest about funding contributions should be directed to Melanie. Before we get to the phase 3 discussion, we have one more talk by Brian, which should hopefully answer all your questions about the new correlator. And thank you all.
Thanks very much, Mia. I'm just looking through to see if there's any hands up. No hands up. Any questions from everyone or anyone?
Ramesh has a question.
Ramesh has a question.
So the issue in that you both mentioned,
Yeah.
we said that it has flexibility to sort of data management. Is that going to free up some significant amount of petabytes from this archive?
Yeah, so the question's about Crucio, which is the data management program, and we're still in the very early stages of investigating this, but that would hopefully be able to free up some space if anyone in the data management team wants to speak on that.
I don't think it'll free up space per se. What Crucio potentially does is allows different options in phase 3, and this is pertinent to Miguel's comment before. So at the moment we have a long-term archive which is at Pawsey and provided free by Pawsey, and we've, as been discussed, we're up against the wall of the size of that thing. I should say, by the way, Miguel, we have asked for an increase in 10 petabytes of data to that storage to Pawsey, and I've asked for that for the last 18 months and it's been delayed. Pawsey has folded that into their capital refresh program, and so it's been pushed back. We've also been asked by Pawsey to put forward what we would need to operate phase 3 over this time period of 5 years, which was something like 200 petabytes, according to the modelling. So we are doing those things. However, what Crucio potentially does is allows us to distribute the MWA archiving away from just Pawsey and have it managed from different sites. So there is the potential for phase 3 partners to contribute not just receivers and cache and so forth, but this question of the archive then comes into play. So I think that's the real advantage of Crucio, is it's an end-to-end management system that allows a distributed archive, which is exactly what CERN uses. So that's why it's exciting. And we should also highlight the fact that Pawsey is putting in resource for this project. So in addition to working with CERN, Pawsey's put in 0.6 FTE till the end of the year to help us realise this project and see whether or not it's a suitable path forward for MWA, which opens this archive question, I think, in a really interesting way for partners. I'll come back to this in the phase 3 discussion.
Excellent. Okay, it doesn't look like there's any more questions, so perfectly on time. Thank you, Mia. Next speaker is Brian Cross, talking about the phase 3 MWAX correlator. Go ahead, Brian.
Hi, good morning, good afternoon, good evening to those of you in those parts of the world. Yes, as has been introduced, I'm here to talk mostly about the implications phase 3 has on the MWAX correlator, and to drill down a little bit into the differences that the researchers would see between a complete new set of receivers and maintaining the existing receivers merged with new receivers that were running in a legacy compatibility mode. But before I drill into that, the first thing I'd like to make very clear is the important distinction between what the correlated design supports versus what the hardware that we purchase it to run on supports. Now we've tried to keep the correlated design as flexible as we can, but inevitably we were forced to commit to some assumptions, and I will talk about some of those shortly. Hardware, on the other hand, is hardware. So even if we have a correlated design that could theoretically handle 300 megahertz of instantaneous bandwidth, for example, and it can, theoretically, that would require hundreds of machines. And I don't think any of us think that that's a realistic scenario. So there are strong implications for not just the correlator design, but also the hardware in terms of what do you get out of the system. And I'll just flick to some of the potential hardware bottlenecks. This is by no means an exhaustive list. It's very much an including but not limited to list. And the main one of these that I'd like to point out is that first one, the receiver capabilities. Our existing receivers, Mia said, have served us for almost a decade, but they do give rise to the 1.28 megahertz wide coarse channels that are critically sampled and unfortunately have the problematic bandpass edges that I'm sure most of you have had to deal with or haven't been able to deal with, as you see. The voltage network system is how we get the data from those receivers into the correlator. It's actually quite a high-speed network, and we need to ensure that it handles the instantaneous bandwidth we need. The MWAX servers that we purchased themselves, and I'm going to blow that up on the next slide. From that point in the signal chain, the data volumes are largely determined by the observing mode. So it depends a lot on how you have the dial set in terms of frequency averaging and time averaging, but you still need to be able to bring that data down to Perth, ingest it into Pawsey, get it onto the tapes. And then there's the post-processing, the cotters, RFI flagging, and even the science pipeline requirements. It's no good getting all this data down if we have no way of storing it or processing it. So when we looked at the receiver capabilities and we said, well, we need to allow for the possibility of having to keep the existing ones in, we were able, I say we, it was mostly the work of Jake Jones, in having our proposed new receivers support a legacy mode where they were able to produce data that could be cross-correlated with the existing RI receivers. But it is important that everybody understands that that comes with the same 1.28 megahertz bandwidth coarse channels and the same bandpass edges. So they do not disappear unless we move to an entirely new receiver group. Now this is the hardware server requirements that were given to the board some time ago. At that stage, the mandate was for hardware which was capable of correlating 256 or more of the existing legacy tiles, the hardware that would be required for our existing RRI receivers plus other receivers to fill out the 256 running in compatibility mode. We didn't ever purchase the set of servers for these, of course. That would be a substantial part of the budget costs for the new correlator. But we were able to do some actual testing through the use of some try-buy machines and some loan machines from partner organizations, HP, Dell, Supermicro, and we were able to verify in practice that the hardware spec that you see there was sufficient for what it needed to do. That means that it could ingest the UDP packets fast enough with an acceptable bit error rate. In voltage capture mode, it's capable of streaming those raw voltages to disk in real time. There was sufficient PCI bandwidth for moving the data to the GPU, sufficient GPU capability, computational grunt to be able to perform the FFTs, the cross multipliers, do channel and time averaging, local visibility storage, all the things that are necessary. Now, some of those would seem at first blush like they would be easy to meet or easy to fit in with. PCI buses, for example, have some very impressive numbers for their bandwidth. But when you drill down into the details and you see that libraries that we're using, like the XGPU library, assume that they are pulling all of their data over that PCI bus in the form of floats, whereas in our case, it already was in floats on the GPU. So that was an enormous amount of PCI bandwidth that would otherwise have been needed. And thanks mostly to the work of Ian, he's managed to convince the software to be able to use local buffers. So some of these hardware requirements can be addressed by smart software changes, and some of them you basically just need to buy the grunt to do it. the one of those which was perhaps the closest to the wind, we were on the comfortable side, but only just on the comfortable side of what was acceptable, was the disk write speed for the voltage capture. Each one of these servers needs to write an entire course channel to disk in real time in voltage capture mode. For 256 of the legacy tiles, that means we have to average a sustained 1.3 gigabytes a second. And we were able to get about 1.6 gigabytes a second. So 1.3, and we were able to get 1.6. And that is while everything else is happening. And I'll stress again, that is real sustained write speed. It won't surprise any of you to know that. Those numbers are actually very different from what the disk drive and RAID card manufacturers list as their maximum transfer rate. It makes some very good use of caches and things like that. But in our case, we need to be able to keep it up for tens of minutes, half an hour at a time. So that's what the hardware specifications we were looking at that time. And those hardware specifications are fully applicable still to the 256 tiles in a legacy configuration. Now let's just flick a little bit to those correlator assumptions that I mentioned earlier. So again, absolutely not an exhaustive list, just a couple that I want to point out here. The first one is that our time blocks of data can be carved up into 40 millisecond sections. That allows us to combine whole multiples of 40 milliseconds for our time averaging. That there is a whole number of fine channels that fit exactly into a coarse channel. The assumption in MWAX currently is that you can do that there is 128 exactly 10 kilohertz channels in 1.28 megahertz bandwidth. That coarse channel width is the same for every coarse channel, that whether you're at the bottom of the band or at the top of the band or wherever you are, they're all the same. Be that 1.28 or something else, nevertheless, they're all the same. And a related but slightly subtly different assumption is that the interchannel spacing between those coarse channels also is constant. That's fine. But then came the possibility of oversampling receivers. And if we look at oversampling receivers, then one of the things that we would ideally like to get away from is some of the bespoke hardware design. I think there's good reasons why the people a decade or more ago used bespoke designs. There was not a lot of commercial off-the-shelf hardware that could work at the speeds that needed to be worked. That's not the case today. But one of the things we were anxious to get rid of is our rather unusual 655.36 megasamples a second sampling rate with our very strange 163.84 megahertz distributed clock. We want the new receivers to be able to use commercial off-the-shelf standard phase-locked loops, or to be able to be produced from standard components and phase-locked loops, and basically be able to give them something a much more normal and regular system, such as a distributed 10 meg reference system, and for it to generate the sampling clock itself locally. 800 megahertz, megasamples a second, I should say, is a good number. It gives us slightly more bandwidth at the top end, not that our antennas go up that high particularly, but it's very easy to generate and quite a standard one that lots of people use. 256 coarse channels. We're talking about FPGA resources. There's all sorts of good reasons to keep it to be powers of 2, and I don't think that creates a problem for us. And that oversampling ratio that we show there, after looking at a few of them, gives us some really nice packet sizes and time alignments on 1 second boundaries. And the bandpass looks great. Some of you will have seen that bandpass before. Those of you who are interested, we can talk about that offline, or I can send some details around. But those numbers together strongly imply that in an oversampled receiver that we are likely to see for phase 3, that the coarse channel width would move from 1.28 megahertz to 1.5625 megahertz. Okay, I'll say that again. Our coarse channel width is likely to get wider. But hold on, I hear you cry. Didn't I just say a couple of slides ago that we have an assumption that the fine channels fit, a whole number of fine channels fit into a coarse channel? And if you have rather strange looking number up there, coarse channel. How can you fit in 10 kilohertz or 20 kilohertz or 40 kilohertz fine channels? And the answer is that you cannot. And that unless we change something, that is exactly what it means. Now, Mia mentioned very specifically in her talk earlier that we are after some feedback from the collaboration, from the data consumers, and this is very much one of the things where I think we need in the ops team and the development team a better understanding of what requirements you guys have for those channel fine channel spacings. If we look for a minute at the allowed fine channel spacings for the existing receivers, you get, in fact, there's more than this, but you get some quite nice, even looking numbers. I have to say that although there's a lot of problems with the 655.36 megahertz sampling clock that we currently use, it's non-standard, but this is very much where it shines. You do get some really nice fine channels. Now, if we compare and contrast that set with what I'll call the native fine channels that you would get in a proposed oversampling phase 3 MWA receiver, you've got 1.25 kilohertz, 2.5 kilohertz, 12.5 kilohertz, but you don't have the 10s, the 20s, and the 40s. So as we switch to those oversampling receivers, we are expecting, unless we make some other changes, that people would no longer have access to those frequency sizes. And again, I hear you say, well, if we've got 2.5 kilohertz, surely we can just glue 4 of them together and get 10 kilohertz. And indeed, of course, you can. Where the problem occurs is not in the midst of the coarse channels, it's at the coarse channel boundaries, where you find that you don't have access on that particular server to the bits you need to put together the 10 kilohertz for that side. So it's up to the board, it's up to the time allocation committee to decide, incidentally, whether these are all ones that would actually be available to researchers. 250 hertz, for example, has a horrendous data rate and implications for transport and storage. But let's say that this is the list of possibles that we have, we get a subset of. So I pose the question to the group, must MWAX, when running in oversampled mode, support 10, 20, and 40 kilohertz fine channels? If it does, then we have to address it. And if we address it, there aren't a lot of nice options. Good PLL generated sample rates and oversampling ratios don't grow on trees. I'm not saying we couldn't find another combination, but we can't throw infinite amounts of FPGA resources at it either. One option is to make individual coarse channels different widths. So instead of having them all, say, 1.5625 megahertz equally apart, we could have our coarse channels be 1.56 megahertz, 1.56 megahertz, 1.56 megahertz, have a string of those, and then every 16th coarse channel would be 1.6 megahertz. Okay. Now, that solves the problem of the 10, 20, and 40 kilohertz, but it has non-trivial implications for other parts of the system. It certainly has non-trivial implications for the work of Greg, for example, and the cotters and the systems further downstream, but it may also have serious implications for you guys at the very pointy end of the data where you need to use it. So if we are in a situation where the 10, 20s, and 40s are necessary, then my question would be, how do you feel about the prospect of different coarse channels? But I stress again that the current correlator as it is does not support 10, 20, and 40 in the oversampling mode for the oversampling ratios we're proposing to use. Okay, so just for a moment, let's assume that those channel widths are fine, and we're keeping with the 1.5625 channels, they're all the same. Then let's just go back to our disk speed. So we've now got coarse channels which are wider, and each of them is oversampled. This is a substantial increase in the data volumes, where before I said that 256 tiles required for each server to be able to write to its disk. 1.3 gigabytes a second. In the case, and we were getting 1.6, in this new world, it needs to be 2.1 gigabytes a second. If we look at those hardware bottlenecks again, obviously this affects the receiver capabilities, but anywhere that it's dealing with voltages, so the voltage network system, the ingest rate, the disk write speed we talked about, the PCI bus performance, and the FFT rate, all increase by 56%. At that point in the signal chain, you can lose most of the overhead of the oversampling, and then you're dealt with only with the increased data caused by the fatter channels for the XGPU, frequency time averaging, the links to PAWSI storage, and things like that. What we're hoping to provide, though, at the end of the day, is for 24 course channels in an oversampling mode, each of them to be wider than the current ones, each of them to be 1.5625 megahertz wide, for a total of 37.5 megahertz with usable channel edges. Okay, so when we're talking about the difference between another set of legacy receivers to augment the existing ones versus an entirely new set of oversampling receivers, I think this is what it probably means to the researcher at the end of the day. Now, we don't have a go-ahead now to buy all this equipment, and to be honest, the situation is likely to change between now and then. It's certainly changed from the last time we checked prices out, Australian dollar, COVID supply lines. Moore's law is on our side. There's Ampere class GPUs to be available, expected in the next few months. So we can't really be certain that we will meet these specifications at an acceptable cost when we actually go out with our checkbook to try and buy the new servers. But I think we are within the ballpark of what we would expect to get. So I'll leave it at that point. If there's any questions, thank you.
Thanks very much, Brian. Yeah, perfect timing in the end. Questions, let me see. Divya has his hand up, and then we've got some questions in the chat. Go ahead, Divya.
Yeah, hi, a very nice talk, thanks. What sort of time resolution are we hoping to provide with the correlator, the highest time resolution?
Well, here we just have distinctions again between the knobs and dials that the correlator supports and what the time allocation committee and the board would allow you to use. As far as the correlator system itself is concerned, not the hardware, then it's possible to dig down into a single 40 millisecond time slice. But that just produces ridiculously large volumes of data. So I expect that what you would see is something like 200 millisecond as being the smallest time slice that would in practice be available. Even at that rate, we're likely to be generating data far faster than it can be ingested into PAWSI. But thanks to the good work of Greg Sleep, we have some cache boxes that can swallow the data at that rate and then dribble it down to PAWSI for the ingest. So I think in practice, the answer to your question is probably 0.2 second time resolution.
Great, thanks.
Divya. John had a comment that I'll let you respond to just in the chat, Brian. Then there was a question, I guess, from Luke. Wouldn't the different channel layouts, wouldn't different channel layouts change how you can compare observations with phase 1 and 2 data? Is this a problem or is this okay? I
guess that's exactly my question. Well put, thank you.
Right. All right. So good follow-up question. Kath says EOR would like to have all of these scenarios provided to us. I guess you mean possible observing modes, and so that we can do some simulations. Wider course channels means first harmonic moves further into the EOR window, which is not desirable, but we would like to be able to model this. So I guess that's the same comment.
And indeed, maybe that might affect whether we go for the 256 or say 512. Although, you know, there'd need to be reasons for that. But certainly, Kath?
Yeah, well, that would actually be really useful. I mean, I think having had the design work for the Correlator Advanced as far as it is, The purpose of having this talk and this session is to communicate back to the collaboration, you know, where we've got to on the technical side, and then to seek feedback on refining the actual implementation. So I think for this and also for phase 3, what we'd really like to do is provide the documentation that have been written to members of the collaboration that indicate interest to seek feedback from the collaboration on exactly these things. So yeah, Kat, that'd be excellent. And if other groups want this as well, they should let me know.
Yeah, just a quick comment. So I don't think from a pulsar point of view, it is nothing psychoscientific channelization and software are generally used to working with a whole bunch of constraints. So I think it is very useful. The oversampling is what will essentially help us to get uncorrupted data as a function of frequency, but channel, it can be any options that you can use from the constraint. Thank you.
Yeah, we didn't really hear that, but it sounds like there's a general consensus that the observing modes need to be shared out and for comment. So Melanie, did you want to move on? Or do you want to, there's one more question in the chat.
I think we can have the questions, Randall.
Yep, so there was a question from Harry to Brian. How do you expect to address the FFT scalloping when using CUDA FFT on the GPU for the fine channelization?
That's very much in Ian's bailiwick. I would like to, I don't think Ian's on, but I'd like to take that one under advisement, if you don't mind, or pass it on to Ian Morrison, who's responsible for that part of the correlator.
Yep, and Miguel has his hand up.
Sorry, so great talk to you guys. Really enjoyed it. So I'm actually raising my hand to do work. So it turns out, and this is just evolving, but both with looking at the MWA current system, and it turns out the Hera and Meerkat systems, it turns out that there's frequency of structure associated with digital nonlinearities, which at least I hadn't really appreciated before. And that is actually a much larger source than I thought before. So we're trying to hunt down exactly what's going on. We're learning rapidly. This is very much breaking. I essentially raised my hand saying the overall system looks great and stuff like that, but we'd love to be of help and help work with some of the stuff we're learning on the digital nonlinearities and how that comes into the frequency as well.
I guess it's a comment more than a question, but yes, we can make available. Clearly, there's a few extra bits in the stream as it is now, and we're hoping that we've solved some of the problems that have led to the rather strange discontinuities on course channel boundaries that we see in the existing one. But nevertheless, it's still we've still got a limited number of bits. I wish I could promise you that everything was perfect infinite precision, but sadly it is not the way.
Okay, and on that, perhaps it's a good time to throw it to Melanie to go to the phase 3 discussion. I don't think you necessarily need me to moderate this, but I'll be here if you need me, Melanie.
Yeah, no worries. Thanks, Randall. Actually, I'm going to get Mia to put back up her slides with the timeline on. So just bear with us for a sec. We're going to do some logistics in the room.
Can everyone see that? Oh, hang on, let me.
Screen sharing has stopped. Okay.
Talk amongst yourselves.
A mild technical issue here.
I can quickly say something that I forgot to say at the start of the meeting. I guess, since we're getting into a discussion, it's probably just safe to remind everyone that, the MWA has a code of conduct. So if there are disagreements, try to remember that. Otherwise, no worries.
Be nice, is what you're saying, Luke.
Exactly.
All right, all good. Can you see the timeline? Okay, it is up. Very good. Excellent, thank you, Mia. All right, so I just wanted to preface this discussion session with a bit of background for people in the wider collaboration who may not have been party to some of the previous presentations and things that we've had. So I think everybody understands that phase 2 is the operational phase that we're in at the moment. And as Mia outlined very clearly in her talk, this is a phase where we've got 2 configurations that we swap back and forth between because of the limitations of our current legacy correlator. That phase is funded to run for effectively another year through to June 2021, as Mia has put here on the slide. And then in terms of the sort of contributions that have come into the project from various national consortia, that's where those contributions cease and we go forward into the next phase, the exciting phase 3. Last year, the board defined phase 3 to be a 5-year phase from mid-2021 through to mid-2026, and this is both an operational and upgrade phase. At the moment, we have 5 countries involved in the MWA, so Australia, China, Japan, the US, and Canada. We've had indications from all of our current partner countries that they would like to continue in phase 3, subject to obviously funding constraints. In the Australian case, as I mentioned in my talk, we've had the outcome of the midterm review of the Australian Decadal Plan for Astronomy, and so that's given a very strong recommendation that MWA be continued to support as a high-level project in Australia. So obviously Australia will continue. The US has indicated through Brown University that they intend to continue. Canada has agreements in place already to continue in phase 3 from their contribution to phase 2. China is very keen to continue, and I'll come back to this in a moment regarding receivers. And we're waiting to hear back from Japan. I don't know if anyone from Japan is online. In addition to that, we are actively seeking new partners for phase 3. So anyone who's interested in participating in phase 3, or indeed old partners like India to return to phase 3. So the purpose of this discussion session is really to outline where we're at the moment in terms of thinking for phase 3 and to present opportunities for people to consider whether or not they're interested in contributing in different ways to phase 3. So as I said, it's a 5-year upgrade and operations period, which starts from the middle of next year. One of the very significant things we have to do, obviously, is get a new correlator. So I don't want to harp on about this, but our current correlator was purchased by me for New Zealand, for New Zealand's membership for the MWA, and installed in January 2012. So it's been in the field for 8.5 years. IBM gave it a 4-year life cycle. So it is, in addition to all of the limitations that it puts on the current observing modes and so forth, which have just been discussed in high technical detail, it's also old, like super old. And as you know, machines that are running continuously for long periods of time with power that goes up and down and so forth have increasing fault rates. And so we are in the regime of needing a new correlator. So this work to design a new correlator is timely. In addition to that, going forward, what we'd like to do is move towards a 256T system. And so for that, we need to have 32 receivers if we can, and we need a new bunch of receivers either to replace the existing receivers, as Mia discussed, and then so remove the legacy receivers and then upgrade to full 32 receivers, or have some sort of interim hybrid system. So that's really what we're talking about. So the MWA operations team has come up with a document to describe phase 3 options. We are very happy to share that with the collaboration. It's gone to the board, but we're very happy to provide that to anyone that's interested in receiving it. There's also a document describing in detail the MWAX correlator design. Very happy to share that as well. I think one of the threads that I want to sort of pull out here before the discussion kicks off is this thread around what the observatory provides and the archiving and so forth, because this is obviously of interest to the science teams, and it is in the phase 3 vision implementation document, but only as a paragraph. So it does provide a different mechanism beyond receivers and correlators to contribute potentially to phase 3 if the board defines phase 3 in a particular way. So at the moment, we have the long-term archive provided at Pawsey, and that's the only official MWA data archive. Raw data comes down from the site, it gets distributed through the ASVO to the collaboration. It doesn't have to be this way. We could potentially have a distributed archive system in phase 3, and a successful Ruscio project, as I've highlighted already, may open the doors to that. And the reason that I bring that up is that I'm aware that a number of current partner countries and future countries see the MWA as a pathway to SKA and have access through their national SKA opportunities to look at data transfer and storage using MWA as a precursor for that, not just for science, but actually how you move SKA data around. And so it may be that there are opportunities there to have a distributed MWA archive, which removes some of this pressure that we've been discussing on the data lifecycle potentially, and also provides redundancy and other I think things which are really interesting and beneficial. So I put that out there. It is subject to us getting a successful completion of our Ruscio project, but if you are in possession of a large SKA data center in your country, which has currently not got any SKA data in it, and isn't likely to for many years, we can help you with that, potentially. And the last thing I want to comment on is whatever happens beyond phase 3 is obviously TBD. The SKA has put in their operations plan that they expect the MWA to be around for SKA verification and commissioning and benchmarking. So it would be nice if we could actually continue from the SKA perspective. But also we are obligated as an observatory to serve out the data collected on the last day of MWA operations for a year and a half. And so that's why there's this blue arrow that Mia's put there, which says, you know, from the end of phase 3 in 2026 to December 2027, we're still required to operate the ASVO and serve out data in the long-term archives. So we've actually put all that in the Pawsey planning. Now, that's not to say that things can't go, you know, we can't have a phase 4, but right now that's what it looks like. So that's the full life cycle from now. So I guess what I want to do in this discussion is 2 things. So seek feedback from members of the collaboration on the overall plan that we have here, and find out who's interested in receiving the detailed documentation to describe some of these things, and to just open it up for questions and comments from the collaboration. So that's how I intended to run this session. So I'm happy to see if there's any hands up. It's difficult for me to moderate this and drive this thing here and see what's going on. So Luke, are you there? Can you moderate this for me if there are questions?
Yeah, sure.
Ta. Are there?
Not from what I can see.
Oh, well, Divya.
Oh, no, wait, yeah.
Yeah. Hi, Melanie. Thanks. Yeah. So the last thing which you mentioned, which was about trying to use the opportunities for setting up the regional SKA centers to engage with the MWA project, is exactly the route which we are trying to take here in India. It has just so happened that the proposal has been stuck with the funding agencies for a while, and we are sort of trying to see what we can hear back from them. That's exactly what we are trying to see, and also use that as an opportunity to not just to demonstrate data transfer, but like you said, to alleviate the storage requirements at the Pawsey Center. So I'm hoping that something will move on that front. And about the request for documentation, I would like to put in the shy request to have the documentation for the correlator design as well as the phase 3 planning.
Yep, absolutely. I think both those things are really good to hear. And in fact, I did note on your slides yesterday, Divya, that you had a line suggesting this was in fact the route that India was taking for considering rejoining the MWA. So that, right, I think is a really good outcome. And it also comes back to our discussion around the current data sizing issues, because my understanding was that you were also seeking to move the shy data, or a large part of the shy data, to India in the near term, as we discussed at the end of last year.
That remains true. However, the proposal which we had put in for that is still pending with our funding agency.
Right.
So I can't make any definitive statements about a timeline or what that data volume might be, but the intent certainly remains the same. Yeah.
Yep.
Hi, Divya. It's Greg here. Can you hear me?
Yes, I can, Greg. Yeah.
So I have you in mind as perhaps one of the first experiments with Rusho and moving data internationally. So as the project progresses and we determine the capabilities and the suitability of Rusho, I'll keep you in mind, because maybe your proposal and this project can sort of meet up in the middle somewhere.
Sure. Thanks, Greg. Much appreciated. Yeah. Thanks.
I see that Nick has asked a question in the chat. What happens to the archive after ASVO support ends? Well, if ASVO support ends, then the MWA has ceased to exist. So in one sense, that's not our problem, but in the other sense, that would be up to the grace of Fawzi, I suspect, or whatever incarnation Fawzi exists at that time. So I can't really answer that question definitively, Nick. All observatories come to an end at some point, and what happens to the data, I think, depends on a number of factors which we can't predict at this stage.
Nick, Melanie, can you actually move a bit closer to the mic?
Well, yes.
Cool, that's all good.
Is that better?
Yeah, Nicole has a question.
Yep.
I was wondering if there was going to be a period of official community feedback for policies or plans for hardware changes and stuff like that. I mean, you can consider this like an official community feedback right now, but in terms of allowing people to go away and think about it and have paper documentation about what each of the changes are going to be, that might be helpful.
Well, I mean, that's what I'm proposing. If people want to have a look at the documents that have been written, I'm asking for them to nominate that themselves now. We will, we haven't got any money for a correlator at this stage. We have a funding request that went in last May, and recommendations for that funding have gone to the minister in Australia, but we don't know what the recommendations were, and we sit at the pleasure of the minister as to when that will be announced. We're hoping that that will be before September. So I'm very happy at this stage to provide members of the collaboration with the technical documents and with a limited time period to make comments on them. So yes, effectively, that's the start of what this is. With respect to phase 3 and the receiver work, this is a good segue for me to talk about the fact that Xiao has been working with the MWA team and engineering team here at Kyra to develop a very significant proposal for new receivers as part of China's potential future contribution to phase 3. And that was put to the MWA board earlier this week. I received it last Friday. It's an excellent technical document. Randall was heavily involved in negotiating and leading that process with Xiao, and the proposal is that they would provide 16 new receivers. And so on this timeline here, where it says receiver prototype tested and design finalized, that is the Xiao receiver design. So again, if people want to have a look at this very high level proposal, which I think is very good, I'm happy to provide that. And I'm sure they're happy to receive comments back on the order of the next month or so. But it does look pretty good to us. Now, I should say we have pursued a number of different receiver pathways over the last few years. So there was a significant piece of work that was done by Jake Jones and members of the ops team and engineering team here at Curtin working with National Instruments and their now distributor in Australia, Braymac. And that's a very nice system as well, but it is far too expensive. So you're sort of looking at a factor of 3 increase on the cost of the receivers. And so unfortunately, we don't think that's a viable option. And in addition to that, there's been some other bits and pieces done. So I think we're very happy to have feedback on the work that's been done to date. If anyone wants to sort of provide comments about specs that they don't think have been met or so forth and can be reasonably contributed and adjusted in the current work, that's fine. If there wants to be some sort of, individuals want wholesale changes, I think that would be more difficult to accommodate, but certainly providing feedback on the current specs, I think is okay. Randall, did you want to, or anyone in China who's online from the shower engineering team, want to say anything to that effect regarding the shower receiver design work?
Sorry, Melanie, you caught me mid-Danish.
Ah, sorry, I can't see. So you come in and take a Danish.
There's only one place that Danish is going. Not really. I mean, to Miguel's comment before about the specs, or I guess requirements of what we're trying to achieve with new receivers. These high level, what I would sort of call requirements, but are not really requirements, haven't really changed, since I was presenting them 4 or so years ago.
Yeah.
The goals, the things we're trying to address are the same, the coarse channel edges, and to Miguel's point about the bit depth and linearity of the system, we know that these are issues. And so the core requirements of what we're trying to do is increase the bit depth, have the oversampled filter banks so that we can get rid of the coarse channel edges. And then everything downstream is about having standardized interfaces and things like that, so that we can have sort of drop-in replacements and off-the-shelf components and that kind of stuff, rather than having the bespoke data transfer that we've got at the moment. So, I mean, there was never any high-level hard specs for what was required, I think. But I think what we're trying to do is just increase linearity and get rid of all of these issues going forward. So I think where we're at, with 12-bit sampling ADCs and proposed 8-bit, out of the receivers, achieves everything that we need there.
Does that answer your question, Nicole?
Yeah, I was actually just typing something into the chat. I think that's great. I think we should probably also have an email out to the wider collaboration, because some people can't be here due to time periods like John.
Yeah, I don't want to have unstructured feedback received. So we'll come up with a mechanism of having collated received, feedback, because I don't want to have potentially 50 people with competing requirements come back, but I'm happy to let the collaboration know that there's an opportunity to provide feedback. So we'll come up with a mechanism for that.
Thanks.
Yeah. I can see that Divya's asked another question there. Is it fair to say that observing will cease at the end of June 2021 and resume once phase 3 receivers and MWAX are in place, hopefully in December 2022? No, we're going to hope to continue observing from the end of phase 2. So from July 1st, 2021, we're going to continue, hopefully. So if we get the money for the new correlator and the design is largely fine, then we can go ahead and purchase hardware relatively quickly, hopefully by the end of the next year, and look at deployment over the first part of 2021. I'm gonna look at Brian and ask, and Greg, and say, is that reasonable? We get the hardware by the end of the year? Yeah, they're nodding. So the critical timeline that I put for the board the day before, is that ideally we'd want to know by September and purchase the hardware as soon as possible thereafter. And then there's a sort of 4 months or so of required development work to finish it off. And then we've got a site trip programmed early for next year, which is to do a reconfiguration. And so we would use that, expand that, and use that to potentially deploy the new correlator system. So I'm hoping that there won't be any significant disruption to service in terms of the timeline. Now, of course, if the current correlator dies, that's a different story. So hopefully that won't happen, and hopefully we'll get funding and be able to sort of go forward with this program as it's currently envisaged without an interruption to service. But I can't guarantee that with a piece of aging legacy software on site where we've got some unstable power and cooling conditions. So we're not actually operating at the moment, for example. We're not observing at the moment because of issues on site with the cooling, so which is damaging to the system. But yeah, no significant interruption of service is currently envisaged.
So in relation to that comment, could you clarify for the next proposal what is the configuration?
Yep. So for those of you online, Ramesh, who's sitting next to me, has just asked if I could clarify for the next proposal call what the configuration is. So the next semester actually starts on the 2nd of October. We're not going to do a reconfiguration in October. We're going to stay in the long baselines all the way through the end of January. And then we'll do a reconfiguration early next year into the compact configuration. So the CPF, which should go out next week, will actually cover the rest of that long baseline configuration. We'll do another one for the compact configuration potentially, because I don't want to put a call out while we might have significant site works to do in February.
How long that compact will
Don't know yet. Haven't decided. So Ramesh was just asking me what happens in semester A 2021, and because of these unknowns around potential upgrades, I haven't actually decided what happens in terms of the length of the call for 2021 yet. Although we do have agreed milestones with AAL, so we would still seek to offer the same amount of observing time as we always do, subject to downtime. What's Kat said? So that means that the archive plot of Greg's will actually increase more. Yes. Yeah, it depends on it. Yeah, obviously this is dependent on the requests that's come in and the schedule and so forth. I mean, this again highlights the fact that we're in this regime of having to do triaging on the archive. And I realize that this is a thing that we've been really lucky not to have had to do before, but we're kind of hard up against it at the moment. And so even though we hopefully will get another 10 petabytes from Pawsey at some point, I don't think that will be until next year. And so we really do need to put in place this data lifecycle policy. And I should say, I just want to really highlight again that we've been through a set of collaboration deletions already, and the EOR team have been really, really good at providing us with data to delete, as have the VCS team. And so we will probably go through another round of project deletions before we implement the actual FIFO queue. So if you're in the other teams, if you're in SHI or GEG, we will be speaking to you about you needing to provide us with things to axe ASAP, so that we don't get into a situation like they have with ASCAP, where they can't actually continue to observe because they can't ingest the data, they don't know where to put it. So we need to stay ahead of that as an actual observatory. Now, as I say, following Greg's talk, in the projected data volume for future proposals going to be taken into account when allocating time. Yeah, so one of the things that we need to do is we've already got a requirement for large projects that they explain how data will be managed. And I would like to extend that in the next CPF to put in a thing where people should estimate how much data they think they're going to collect. So exactly that we can manage this and we can have a slightly better able to forecast when we're going to hit the wall. Because the other thing to note is that data deletion isn't instantaneous. It takes Greg some time to actually purge the system. So Greg, do you want to talk about the rate of ingest versus deletion?
Yeah, up until a few months ago, the deletion process was very slow due to the the straightforward way to do it. But recently I have improved that process now. So I can delete faster than real time we ingest. So that's a good start. But yeah, it's still, you know, to delete a petabyte of data is still a couple of days of processing at Pawsey 24/7 to do it. So it's not as much of a bottleneck as it used to be. So yeah, so basically any time that you can provide a list of OBS IDs that you definitely know are no longer needed, then I'll gladly take them, and within a few days they'll be gone. So.
Okay. Are there other questions or comments?
So Melanie, you
Yes.
mentioned yesterday the possibility of 2 potential new partners. So is there any feel for what, I mean, they both are fairly new into the radio astronomy. So the possible ways they are looking into getting involved. Is there any?
Yeah, so Ramesh has asked me about the UAE and Malaysia and their interest in joining MWA in phase 3. So the UAE, it's through UAEU, and this is through Akib Mon, who was a former PhD student of Stephen Tengace and is now leading a group in the UAE. I think they are indeed a fairly young group, but have an interest in having access to MWA data, and they were particularly interested in space situational awareness, I believe. So they've got EDA 1, they're going to set that up in the UAE and hopefully use that as a testbed for gaining some technical experience. And I think then they're going to try and work out a science program, but I haven't actually been involved personally directly with the conversations with Akib. That's all gone through Stephen, because the funding that they have is actually a joint Curtin UAE project. So that's on that side. It's just there's a component in it for them to join MWA at the level of sort of 1 quanta of what we've previously had. The group in Malaysia is at the University of Malaya, and it's the radio cosmology group there. And they have their own small radio telescope deployed in Malaysia. So I think it's a 6 or 7 meter dish, and they have a number of students and postdocs working on various different radio cosmology projects. In fact, I'm co-supervisor of one of those students and currently a visiting professor at the University of Malaya. So their interest is very much more on the science side, I think, and exploiting MWA science to complement the science that they're doing with other radio telescopes, both the small one that they've set up and deployed themselves in Malaysia and other instruments that they're using internationally. So, but Malaysia has a space agency, and they have interests in building connections in the Asia Pacific region around projects associated with space and SKA and radio astronomy. So in addition to the actual university interest, I met with someone from the Malaysian embassy actually earlier this year who was saying they had a general interest on the government side with respect to science. So those are the sort of 2 areas that those groups would be interested in. But it's mainly in the GEG side, Ramesh, for Malaysia. That's what, if you're worried about they're going to come and do pulsars, I don't think in either case that's their interest. What else have we got? Bart, what are status plans of conversion to RF over fiber? I seem to recall Adam showing some unexpected spectral structure on some of the existing long baseline tiles. Yes, so the board approved an upgrade to, as I mentioned in my director's report, do 2 things. So one was to remove the faulty LMR 400 cable, which had decayed on site and left horrible bits of plastic everywhere, which we did. And 2 was to upgrade to RF over fiber for the long baseline tiles. I programmed money in the budget for that, but I have currently put that on hold pending the outcome of the Correlator funding application. So I've got about $430,000 programmed for that upgrade. It's currently sitting on hold because if we need to buy a new correlator, if we're unsuccessful in our funding application, that's $780,000 and we can't do both. So if we get the money for the correlator, then the RF over fiber upgrade will proceed. If we don't get the money for the correlator, then we can't do it. Does that answer the question? Or we can't do both immediately, put it that way. All right, no one's objecting.
Sorry, I guess I was just wondering about the second part of my question, whether or not like the technical,
The
satisfied with the technical design of the RF over fiber, or whether that it's been validated that it's.
I don't think we've actually, as in the ops team, have actually seen that. So I know that there's been sort of discussion about it, but no one's actually approached us. So if someone wants to provide us with those details, that would be useful, because as far as we know, it should be fine to proceed. But the project's on hold, so there's time to look into that. Other questions? Luke, has anyone got their hand up? I can't see people. I can only see my timeline.
No one's got their hand up from what I can tell.
All right. Is there anything?
There's stuff people are saying in chat now.
Yeah, don't read the stuff that's with the red on it, Luke. Okay, so Kath says, thanks to the ops and management teams for all this great phase 3 work. It's exciting stuff. Thank you, Kath. And thank you for being proactive in helping us delete data so that we don't have as big a archive crisis as we could have. All right, Adam, if you find your old notebook, please send it to us, the stuff that we need to look at.
Yeah, and I think I may have deleted some of my locally downloaded data, so reproducing this is more difficult than it should be.
Need a FIFO Adam.
There you go. FIFO queues save everybody. Well, I'll just ask Randall. Randall, do you have any comments on this Ripple issue, this RF over fiber issue?
Yeah, I didn't know, interesting that Adam had seen something. The comment that I have on this is that a year or so ago, we installed the cram tile in the middle of one of the hexes, and that uses the MWA RF over fiber, but on a shorter run, it's on about a 200 meter cable fiber run. And there were some puzzling ripples there that we have only recently just started to investigate. And I mean, from what we've found, that there is reason to think that there is some sort of reflection ripple-y type thing on the RF over fiber cables as well, but they can be removed with optical isolators. So we're still looking into this. I've got a student who's doing this as a separate project, and he's going to be finished in a month or so, and we'll write this up. But yeah, I think it's something we need to keep an eye on, and hopefully I'll have a report that I can share with the collaboration within a month.
Okay. All right. Is there anything else the ops team want to point out that I've missed? They're all shaking their heads in the room here with me. Oh, Greg.
Yes.
You move to the microphone.
So in the current new correlator design, the visibilities that get generated are stored as floating point values. The existing correlator that we have at the moment delivers integer values, which are very easily compressed. So since 2017, all the data coming out of the correlator has been compressed, and we get a reasonably good compression ratio of about 2 to 1. And so the 2017 and beyond data takes up most of the archive now. So we're actually storing a lot more than 38 or 34.8 petabytes. We're probably storing closer to 50 or so at the moment in terms of real data. But with the new MWAX correlator designed the correlators producing floating points, which are not compressible. So that is yet another data challenge for us, is that at 256T, we're going to be looking at, double the data rate for voltages and quadruple the data rate for visibilities. But also with the MWAX correlator, we're going to be looking at almost double the size of the visibilities for the same size observation that we would be doing now in the existing correlator.
Yeah, so just to put that in numbers, that means we go from 1 petabyte of data a month to 8 petabytes of data a month. If we get to 256T, we have had some forward modeling that we've given to Pawsey for what that will do to the archive and our needs over the next 5 years. And we've asked for 200 petabytes, not in their current refresh because that's out of scope, but in the one beyond that.
So I guess just as a comment there, that even without full phase 3, we are still looking at higher data rates for the equivalent same observation that you would be doing now. So that's just one thing to be aware of, and something that will keep me up at night, surely. So just a comment, really.
Keeps you busy.
It does.
Gives you a job. It's good. Yeah, Adam says in the chat that he's got a plot he can show us, which would be cool. So, yep, we can stop sharing and you can do that, Adam. In the meantime, Ben McKinley, phase 3 Sene is going to be awesome. Yes, it is. It's going to look very awesome. And it's on you, Ben, to make it exciting. And Charlotte said, are there prospects for online beamforming using phase 3 correlator?
Not as part of the correlator. I know Ian's done some separate work, but it's out of scope for the correlator per se.
Did you hear that, Charlotte? So Ryan is saying that Ian Morrison's done some separate work on this, but it's out of scope for the current MWAX correlator. All right, Adam, did you want to talk to this plot?
Yeah, I'll try. This plot is months old, and I haven't thought about it in a while. But the basic gist of it is I took some lobes data, and it's pretty just random data. Took autocorrelations and delay spectra of those, and then grouped them by the cable type, as you can see in the little inset here. So the RF over fiber is this 4th row here, and there's various spiky things. I don't claim to understand most of it. In fact, a lot of the kind of structure in all the different cables is a bit confusing to me. There are various negative dips that I don't understand, but I believe that that's what was referred to as this plot that I had shown on an EOR telecon a while back. That's pretty much it. That's all I got.
Yeah, I mean, essentially that is, I think that's what I was recalling, that basically in this representation, it doesn't look like the RF over fiber really, it is clearly better than the existing cables. In fact, some might say it's worse.
Yeah.
All right, well, it'll be good to send us that and have a discussion about how much it's worse. I mean, the LMR 400's just been replaced. So your top 2 plots, that was the previous LMR 400, which had some issues.
Yeah, and actually it's kind of interesting. You can see the different noise levels from them. Probably some of them decrease.
Yeah.
So.
Okay, well, maybe you can take that up with us offline, Adam.
Yep, will do.
Cool. All right, all good. Oh yeah, what's the frequency resolution, Adam?
Oh, that's a good question. Because I think that they were averaged up in frequency a little bit.
Yeah. Okay. Well, let's collect the known information on this. So maybe look into that later, Adam, and send it to Luke.
Yep.
And we'll get Luke to collate some of this stuff for us to consider.
Yep.
All right. Cool. All right. Very good. All right. Has anyone got anything else that they want to ask or raise? No? All right. So if that's the case, then I will just summarise quickly this discussion before we move on to morning tea. So we've got some detailed documentation on the MWAX correlator that we will provide to people who are interested in a structured feedback process, which I'll sort out next week. The same for the phase 3 document. I'm very happy to provide that to members of the collaboration interested in looking at the phase 3 vision and implementation document that we provided to the board. Again, we'll do a structured feedback process. Adam's going to provide some stuff to Luke on known issues with the RF over fibre, which, as I said, the upgrade is currently on hold. In the meantime, the timeline is we've got phase 2 till the end of June next year. Then we're looking at a 5-year operations and upgrade phase for phase 3. Ideally, we'll have a new correlator in place with no disruption of service if we get our funding through the door in Australia. And then we'd be looking at receiver work with the shower receivers going forward, with prototyping and then deployment and fabrication in phase 3. Okay, if anyone has any further comments or questions on any of that, let me know. With respect to the data lifecycle policy in the archive, as we said, we're up against the wall. Again, I thank the EOR team and the VCS team for deleting stuff. We'll do a second round of project-based deletions before implementing the lifecycle policy once it's approved by the board. Science working groups, I will send it to you and you can comment on it. I just want to reiterate from Miguel's comment that there are mechanisms in this proposal to stop us, just carte blanche deleting things based on the timeline. So significant data sets can be saved. And my understanding from some background discussions that we've had is that the EOR 2013 data set that you want to save is well within scope of the available preserved part of the queue anyway, Miguel. So that's not actually an issue going forward in the short term. In the long term, hopefully we'll get another 10 petabytes off Pawsey, but I don't think that will be till next year. So I think I'll close it there and say thank you to everyone for participating in the discussion. And I look forward to a successful phase 3 for the MWA, which, as Ben says, will be awesome. So thank you all. And we'll break now for tea early. Luke, when do we come back? Yeah.
I believe that it is only 20 minutes.
Well, they get 25 minutes. So we're back at 20 past the hour, whatever your hour is. So in 25 minutes. Thanks.
Yeah.
So we'll start again in 1 minute. Hopefully everyone's had a nice cup of tea or something similar. Okay, Andy, are you ready for action, mate?
What was that, Randall?
Are you ready to go?
Yeah.
Okay, we might as well start again. So welcome back, everyone. We've got 3 more technical talks from the operations team, and we're starting out with Andy McPhail with a site update. So take it away, Andy.
Thanks, Randall. Hello, everyone. We'll just roll straight into it because there's a fair bit to cover and I'm under pressure because everyone else has been on time and I've never been on time for anything. Okay, so is that working? Yeah. There we go. So the presentation's broken up into 2 central sections, the past activity and our future intent. Over the past 12 months, we've done 13 site trips, 9 in 2019 and 4 in 2020. The lesser number in 4 were actually equate to 9 because the trips turned into 2-week trips rather than 1-week trips in 2019. And that was simply a response to COVID. The most significant activity that's occurred in the last 12 months has been the ASC upgrades. And a big thanks goes to Dave Emmerich for that. He's finished upgrading all the ASCs in all the receivers. We've commenced the beamformer upgrades, and these 2 activity points are continuing chapters in our ongoing battle against equipment obsolescence. And then there's the LMR 400 replacement. Okay, so the year kicked off with some significant upgrades on site. We had a new transformer installed on site. In the top right-hand corner there's a photo of that. And we also had a field processing facility, which is essentially a RF shielded container on site to do processing. So we had significant boosts in power supply and processing potential capability. And there's just some photos of inside the RF shielded container. We've got 6 racks there with numerous entry points through gland plates. And that will be ready to go as soon as we've got equipment to put in it. Interesting challenges during that site trip. On the left-hand side there, you see a safety valve of the old high voltage transformer. That is sitting on empty because it had an internal oil leak, which only became known when we ripped it out. So we dodged a significant bullet there because according to the techs, it was about a week away from a safety shutdown. We also had a significant rain event just prior to that site trip. And that top right-hand corner shows some of the damage that was experienced to some of our power outlets. They just simply couldn't get rid of the water quick enough. And that lovely photo in the middle is Don Hutton, one of our contractors. The rain event caused a significant bloom of on-site midges, which is a little biting fly which can get in everywhere. And if you're, and that's just an allergic reaction Don had on site. It does look ugly, but that photo that effect just makes him look a lot uglier. It was a good laugh for the whole trip. The August reconfig. The rain event in July caused significant damage to our coax cables. You can see in that top left photo there, some of the damage we experienced to our coax cables. There was a lot of coax replacement on that trip. Hopefully we will not experience that again. We put in some measures to try and avoid that for future reconfigs. In September to October, we commenced a significant period of construction and installation of new arrays, most notably the AAVS2 using the Scala antenna array. The top left-hand corner there, you can see the production team that were building those antennas. It was 10 people, virtually just set up in a factory line type of system, just building antennas and then setting them up on site. top left-hand corner there, you see a photo of the survey points and the antennas being surveyed in, and the array finally installed and commissioned. Oh, sorry. That was followed, once the array was installed and commissioned, we then undertook a 2-week deployment to test the installation of the field processing facility and the new high voltage transformer to ensure they met RF safety standards and emission standards on site. Pleased to report that both installations met the requirements with flying colours. So that was good to get that under our belt. November 29 was fun. The last 12 months, I'm sure you're all aware, have been characterised by climate extremes of all different kinds. That temperature gauge in the top left-hand corner there was corroborated by one by CSIRO. 50 degrees on site working wasn't fun. The only one that really enjoyed it was Steve, our friendly pet goanna there, just sitting down in the sun, just sucking up the heat. He was the only one that really enjoyed November. EDA1 removal commenced in February 2020. You can see there that now the EDA1 ground plane is bare and vacant, just waiting for Ben and Jishnu to reoccupy with their upcoming experiment. And all those dipoles have now been packed and moved and ready for shipment to the UAE. And the challenging event of that site trip was how to replace a flat tyre on a 4-wheel drive forklift when your jack doesn't work. And then March 2020, the reconfig, which characterised by the race to beat the shutdown. As you all know, the shutdown was sort of, in Australia, was characterised by state boundaries being enacted and then internal state boundaries being enacted and enforced. We managed to get on site before the internal state boundaries sort of really kicked in, and then nature, I don't know if this video will play, really decided to put an extra obstacle in our way for the reconfig and just threw it down with rain. And that sort of put it, we had to leave site early again and then try and get back to get the reconfig done. But that was achieved and it was good to have that done. I've talked about, or there has been numerous discussions about the LMR 400. I flagged it at last year's site trip. You can see there, those pink marks is a 10-metre stretch of LMR 400 right from basically that point there. Got 3 of these type breaks. If you can see my mouse there on that LMR 400 cable. And I took that photo because that characterised the extent of the damage of the LMR 400. It was basically 3 breaks in the outer jacket every 10 metres. So that's the previous slide by, I think, Adam, looking at the LMR 400 cable. You really should take that with a grain of salt because that was the quality of the cable that was carrying that data. And this is the LMR 400 cable as it's been removed. There was 26 kilometres of that cable to be removed, which is 80 cubic metres of waste. It's a lot of waste to get removed from site. It costs about $15,000 just to get it removed off-site once we've collated it on-site. If anyone knows of a great method of recycling coax cables, please get in contact because there is a recycler in Geraldton now who has 80 cubic metres of the stuff and would love to get the copper out of it. The challenges during this site trip, I'm not sure if you're aware, but we had some camel issues on site around our solar panel tiles. This is a photo of them. There were 5 of them, 1 bull male, 3 females and a young male. They took up residence around this particular solar panel tile. And we also found one of our coax tiles, tile 118 from memory. The cable was up a tree. The beamformer had been pulled away from the tile. And the camels had a fair bit of fun around that tile as well. That problem has been resolved now. And then coming back from that site trip, finally hit Tar Seal, moving away from site. For those of you that don't know site, to get to Tar Seal is about a 2-hour drive over pretty rough roads. And found these 2 trucks just sitting on the side of the road waiting for their pilot to move this little fella, the biggest, fattest echidna I've ever come across. So him and I sort of played a little bit of echidna soccer there as we gently moved him off the road. But once again, a little bit of fun with the local wildlife. And he was pretty happy because he went straight over to the scrub and dug into some lunch, which is a very large ant's nest that he obviously smelt from the other side of the road. That's him moving off there. Kill that. And then the next animal challenge we had on site, which was the last site trip, was goanna versus coax cable. I don't know why the goanna thought that the coax cable would be good to eat, but he or she certainly took a good chomp out of it. And that was an interesting issue. So that's what we've done in the last 12 years. They were just the highlights, obviously, of the 9 site trips we did in 2019 and the 4 of 2020. Every site trip involved general MWA maintenance, the replacement of tiles, replacement of dipoles, the fixing of LNAs, general cable issues. But those were just some of the highlights from the last 12 months. In the next year ahead, we're looking really at the solar panel tiles in the first, well, was in long baseline configuration. If you look there, this is a charge versus load voltage difference. On the left-hand side of that slide, you'll see that the charge versus load voltage difference pretty much stays uniform. Move into compact array, there's no change. Move into the second iteration of extended observations, and we have some significant changes in the charge versus load voltage. Got those purple spikes appearing and the brown sort of colouring down the bottom. That's indicative of 2 separate faults. We thought we had a handle on it, and then it reappeared again in the current extended observation. It's caused by this particular, the fault is exhibiting or showing up in this particular fault, which is a bridge rectifier and some burnt out jumper cables. We've got a heat issue there. The question is, why is it appearing now in this extended and it didn't turn up when we first rolled out the solar panel tiles? We've since audited all the tiles and tested the batteries for resistance levels. We've noticed that the resistance levels have increased. So we're working on a couple of theories at the moment that the bridge rectifier is not strong enough or capable of dissipating or handling the heat from the higher resistance levels of the batteries. Maybe there's poor crimping in these cables, or maybe the batteries and the higher resistance levels are influencing in some other way. But what we need to get a handle on it pretty quickly, because the moment this bridge rectifier blows, it causes the batteries to discharge to a greater depth than is necessary. And we've just replaced 10 batteries across the 200 batteries on site. And that's a big task. It's down to my trusty trolley Wilson and myself carrying a 50-kilo battery out to some of the solar panel tiles, and there's 4 of those that need to go out there. So it's a good workout. If anyone's looking for a workout, please put your hand up, and I'll certainly give you a 50-kilo battery to carry out there. The next key thing that I'm working on, or that the ops team are working on for the next 12 months, is power infrastructure improvements. So every 12 months, we shut down the site for a few days to do an electrical safety week where we check everything. A year ago, we found the power supply surface laid field cables to some of our non-MWA arrays were degrading. So you can see the jacket degrading there. The electrical contractors gave them a tick in the box and said, you've got to replace them in 12 months. 12 months rolled around and they've gone, no, when they're not safe anymore. So for the next 12 months, we're going to be working on improving the power infrastructure, distribution on site, and a byproduct of that will be that we're going to implement what are going to be these antenna test sites. So 15 and 12 will be small sites that will be supplied with a 48 volt, approximately 1 amp power supply connection. We're still working on that at the moment. For anyone in the collaboration group to conduct any form of engineering or tests of antennas or detectors, should they so wish. So what we're essentially doing in the ops team is throwing it over to collaboration partners that have a engineering bent that want to develop and test their own detectors or antennas on the MRO. We're establishing these sites with a uniform power supply, so that all you have to do is develop your detector or antenna and we can get it out there on site for you. It's not a new capability. We've done this before for Curtin postgrad students and projects. But what we're establishing here is the previous instruments and antennas had always come with their own power supply system, and it was always a different power supply. So we ended up managing a whole lot of orphan power supply systems. So what we're essentially doing is creating a uniform power supply system that everyone can use, and they don't have to go and get EMC tested every time. They just have to test their antenna or device. The next thing we're working on the next 12 months, and Randall and certainly Mia and Melanie have touched on it a bit also, is the RFOF modules. Randall has touched on it in terms of the rippling effect. Myself and Dave Emmerich are looking at in terms of the gain differences between poles over the same length of glass. And what we're trying to do is isolate where the problem is by ruling out what it is not. So we're going to be going up on site over the next 12 months and testing the RFOF modules, the MWA RFOF modules, their transmit power, testing the glass for faults, looking at connections, just trying to isolate where and why this fault is occurring, just so that when the director and the board make the decision about RFOF in the remaining coax, they're fully informed about the benefits and cons of different RFOF systems and the problems we have at the moment with the MWA RFOF modules. Other improvements to capability of the ops team's undertaking this in the next 12 months. We're gaining certification to operate UAVs on the MRO. There'll be 2 qualified pilots within the team. And the purpose there is to hopefully get our own UAV at some stage, to attach some kind of transmit device to it, so that you can conduct, if necessary, some calibration tests or anything that you need to do of those engineering or development instruments and antennas that you wish to deploy on the MRO. We're also developing fusion splicing skills or field fusion splicing skills for improved RFOF management and installation. So that's us getting ready for stage 3 and RFOF installation, should that button ever be pushed. I'd also like to, I think there was a talk yesterday which mentioned problems with tiles that they were discovering in their data. If you do, while you're doing your analysis in your data, and you do find a problem with tiles that's not already listed in your observation ID supporting information, please send us an email. I do try to visit every tile twice a year, but sometimes minor faults that you just simply don't observe, such as cracks in the worlds of dipoles, we just simply can't see. So if you could tell us that there's a problem in the tile in the data that's not in your OBS ID, it would be great for us to get out there and go, right, there is a problem here. We can't leave until we find it. Other than that, I'll close off. I've got a minute left. That's awesome. With our email address, please, if you have any questions or any concerns at all, just reach out to us. We're here to support your efforts, and we'd truly like to get as much feedback from you guys as we can. Randall, over to you for questions.
Thanks, Andy. Good timing. Question from Ben McKinley. Great idea about having uniform power supplies. What about getting data back to the network from them?
Yeah, I did miss that, Ben. Thanks for that catch. My plan is, or our plan is I'll use 12 and 15 as an examples, but I'm developing a few others. At each of those points, there will be either a RFOF or a coax connection back to wherever the processing of that data or the next transmission point will occur. So I want to establish both methods of RF transmission at each location point. So let's use 12 there as an example, so that any particular developer of an antenna or a detector of some kind is not limited to what type of RF transmission system they can use on site to get their data back. Obviously, it depends on what type of RF system, RFOF we're going to use, whether it's a short run or a long run, and the module and all those kind of engineering questions, which will go back to the engineering team supporting the development of the antenna or the detector. But there will be a fiber point there, and there will be a coax point there, and data.
Excellent. Ben says thanks. All right. Well, unless there's any burning final questions, we'll move on. I can't see any more questions. I think the next talk is Andrew. So Andrew, you want to load up? Thanks, Andy. And we'll take it away with Andrew Williams talking about getting the MWA to produce the data you want.
I'm going to be talking from down here, not on my laptop. So, yeah, this is all about what to put in Part C of your observing proposal, how to get me to produce the observations you want. And feast your eyes on those logos, because that's the last thing you're going to see that isn't black and white text in this presentation.
I can't see a screen, guys. Are you sharing?
No, that's my bad. 1 second.
I'm wanting to feast my eyes.
Okay.
Yep, good, thanks.
There you go, pretty logos. Okay. As I said, I only see your observing proposal after it's been accepted. So I don't need to know why your observing proposal is wonderful, why it deserves telescope time. That's already been decided. My job is to actually schedule the observations that get you the results you want. And it's easier for me to do that if I can understand Part C of your proposal, to find out what you want the telescope to do. And with a lot of proposals, that's really hard because the bits that I need are buried in stuff that I'm really not interested in. Also, what people want and what they ask for are often quite different. People ask for things that probably won't give them the results they want. So I often need to get back to the people that have written the proposals, ask them questions about what they actually want out of the telescope before I can actually schedule the observations. So I'm going to try and talk about how to put stuff in Part C that will make my life easier. It's an entirely self-interested talk, and hopefully make your results better as well. So first of all, what you want to look at. Make it very clear what your sources are and where they're in the sky. I had one observing proposal that I had to go through 3 times and read every word before I found what the actual source was. It was described as a concept, but not as an actual position or source name. So make it quite clear what you want to observe. And it helps if you put where they are in the sky, so I can plan whether to observe it at the start of the semester or the end or in the middle. So if there's more than one source, put them all on a table, put your name and your coordinates and any other data that's not the same for every source in the proposal, And your source names, make sure that the source name you put in the proposal actually matches as is in a Visier search, because often people put source names that have the leading part of the source name missed out, you know, PSR or whatever the leading name is in front of the part of the source name that means it's like duplicates, it matches lots of things in Visier. So make sure your source names are actually unique, and put that and data in a table if you have more than one source. If your source names are from a catalog that isn't searchable by Visier, that's fine. I can use the coordinates, but say so in the proposal. Otherwise, I'll waste time trying to look up by source name. And ideally include RA and DEC, preferably in hours, so that I can actually compare that to the sidereal times when I'm doing scheduling. I know radio astronomers love RAs in degrees, but I'm an optical astronomer. I don't think in degrees, I think in hours. And if you have two nearby sources and you want to point the telescope once to look at both of them, then say whether you'd like to use one source or the other, or somewhere in between as a pointing direction if you have any preference. Also, what about when you'd like your observations? Do you want them as soon as possible because you have a paper that's due out soon or you're a student? Or do you want them at a particular elevation? Do you want your source at greater than some angle in degrees, or do you want them in May? Or give me some indication about when you'd like your observations. Just as a sort of general idea, a vague statement is fine, or something more specific if you have more exact requirements. Particularly for large time requests. If you want to request more than 1 or 2 nights, fitting that in with everybody else's observations is easier if I know when you want them and when you need them. So I can't promise to actually fulfill a request like that, but actually knowing what your desires are makes it at least possible for me to fulfill them. And observation scheduling in terms of what order you want things. If you want 4 hours on each of 5 sources at 3 frequencies, how would you like that ordered? There are only a certain number of hours per night. What suits your science better? For example, I might be able to loop over every single source at every frequency on every night. So take lots of short observations, cycling through sources and frequencies, repeating for 10 nights. Or I might want to observe the first source solidly for 4 hours at one frequency, and then the first source for another 2 hours at the next frequency, and on subsequent nights continue that, hammering one source at a time. Or I might want to spend 2 nights just observing the first source, looping over all the frequencies, and then swap to the next source on the next 2 nights, etc. Now, that might not make a difference to you. It depends on exactly what you want to get out of your data. So you might want to consider how a telescope failure or a bad ionosphere for a whole night or a fraction of a night might affect your results. Would you like to lose some of your sources at all frequencies? Would you like to lose some of your frequencies at all sources? Would you like to limit your total observation time for all sources and frequencies evenly? So if you're more interested in one source than the others, it might make sense to spread that source over multiple nights. So a failure on one night isn't going to lose all of that source. The other question is time variability. If there's some sort of time variability, how would you like to sample it? Would you like each source observed on a single night so that you capture scintillation, so that you freeze the scintillation on that night, or would you like it observed over the course of a week? Now, inside each single block of observations on one night, it's easy for me to schedule observations that loop over pointing first and then over frequency. I can do the reverse, but my first default is going to be looping over observations and frequency. That's on a single night. If you over multiple nights, it's completely open. Daytime or nighttime is another issue. If you request observations of a source that simply is not up in the nighttime, then I can schedule observations in the daytime for you. Or if you've requested more hours than are available at night, then I can schedule some in the day. So the scheduling software attempts to optimize the signal-to-noise ratio using Marchand suppress code in the primary beam repository. It chooses a pointing that puts the sun in a beam null without going too far off the source. But it can only really do that if both the source and the sun are above about 30 degrees of elevation, and it works best when they're high in the sky. So that also sets constraints about when and what days and what hours I can observe your source. So think about that if you're requesting daytime observations. The other thing is commensal observing. If you're working with another telescope, GMRT, Parkes, ACCA, anything like that, think about what that means in terms of scheduling MWA observations. When do you expect to know when your ACCA or GMRT or whatever observations are going to be scheduled? When do you know the dates that you expect to be able to do this commensal observing? Put that in the proposal. I will know by September what my dates will be for such and such. How close in time do you need the MWA observations to match the observations on the other telescope? Do they need to exactly overlap within a few hours, within a few days? Does this vary by source? Does it vary by frequency? So think about that and tell me in the proposal. And of course, dishes can often point a lot closer to the horizon than any MWA. And differences in longitude mean that we might see observations that are taken on the zenith at ACCA, for example, but by the time the sky moves around to the MWA, they're right on the horizon or are not visible. So think about scheduling with both telescopes when you request observations with the MWA. And when you do get your allocation results, let me know as soon as possible. Don't make me sort of email you and say, have you found out when you're going to get this time yet? Just be a bit proactive and tell me. Frequency, when you're choosing what channels to observe, MWA observations with a current correlator use 24 coarse channels, where each channel is 1.28 megahertz wide. And the center frequency of each coarse channel is 1.28 megahertz multiplied by the channel number. So every morning we take morning and evening calibrator observations, and the ASVO will automatically use these calibrator observations to calibrate your data when you download it if you want. So if you use one of these sets of channels that we have automatic calibrator observations for, then you are guaranteed to be able to calibrate your data without extra calibration observations that use your observing time and your project ID. So if you use one of these, then you either don't need to schedule extra calibrator observations, or there will be redundant calibrator observations. So using one of those sets means, first of all, you're not looking at known bad RFI. There are some channel ranges that have horrible RFI from satellites. You're more likely to get a good calibrator because we have the existing observations every morning and evening. And the calibrator observations that we schedule for you, if you choose to have them in your project ID, will help other people's observations taken on the same night. So if you do want to use a unique channel set and you really don't want to use one of the standard ones, say that in the proposal. Say, I have considered using this channel set, but I need to use this for this reason. Because if your channel set that you've requested is close to one of the standard ones, I'll be emailing you to say, are you sure you don't want to use one of these? So that will save a bit of time if you say why you want to use a custom channel set. If you, in summary, so what I need to see is the source details, names, RAs, and DEX, what observing requirements you have in terms of channels and number of hours, and what constraints you have in terms of commensal observing and spacing and things like that. And remember that I'm not a radio astronomer, so put the science somewhere else. And the more you can tell me about when you'd like your observations, the more likely I am to be able to schedule them when you want them. Okay, that's it.
Thanks, Andrew. Heaps of time for questions. Just looking through the list. No hands up. Paul says, this is great advice. Can we link to this talk at the time when observing proposals are being requested?
Sounds good.
Yep. Anything else? No? Okay. Well, I guess you all know where to find Andrew if you've got more questions. So let's move on. Next is Marcin. Very good. You ready to go, Marcin?
Yeah.
Okay. Well, share your screen whenever you're ready.
Can anyone hear me and see the slides? And okay.
Yep, all good.
How do I actually turn on pointer? Good morning, good afternoon, good evening, everyone. My name is Marcin Sokołowski. I work at Kertin, and I'm going to talk about the calibration database for MWA All-Sky Virtual Observatory. So this is the work that has been done in this group of people shown here. And as Melanie and Greg has mentioned previously, Harry is currently the new person and he is actually the main ASVO guy now. So he is working on improvements in ASVO, both in the front end and back end side of things. So I will extend a bit on a talk that Chris has given at the last project meeting in December, and maybe slightly from a different perspective today. So you are all aware of the ASVO because you have been using it since end of 2017. It replaced the old ops download script, and now everybody accessing the MWA data, whether it's raw format GPU fits files or CASA measurement set or UV fits file, has to use the ASVO interface. So it provides access to both public and proprietary data. And in 2018, we extended it with calibration component, which is basically the database and some additional scripts which allow to calibrate the final data products. So we had to populate this database with calibration solutions since basically the beginning of MWA, which I consider start of 2014. So with this new interface, you can, and with this new calibration component, you can, if you are using the web interface, you can basically check the checkbox or change a flag in your request file if you use the Manta client, a Python client, to have calibrate to true, and this will tell SVO that calibration should be applied. What happens in the backend is that the system checks whether there is a suitable calibrator in the calibration in the database for this particular for this frequency channel, for this specific observation, and within 24 hours. I think actually now that I see how stable is the instrument, this could be, this 24-hour thing could be loosened up a little bit. So if there is calibration solution, this so Andre added an option to Kotel that it can actually take his format of calibration solution bin file and apply it to the data. So apply calibration on the fly when the data is being converted from GPU fits files to CASA measurement set or UV fits file. So this will happen, and then you will receive the calibrated data set. However, if there is no calibration solution in the database, then basically what will happen, the system will add request record to the table with requests, and basically the script running on one of the operation computers will pick it up and then calibrate and insert into the database. So you will be asked to actually retry this and then you should receive calibrated data set. I know there has been some issues with this, but it's been improving over time, so it's getting better. So basically it all started when I was scheduling observations and dealing with the problems that Andrew was talking about, and I wanted to check what the system is actually doing a little bit more, like by at least having some control image of calibrator fields, and in the same process generating calibration solutions. So I developed a little CASA pipeline which did this, and it turned out these calibration solutions could be used for ASVO. So we started to upload them to the database, and then when we really needed to calibrate lots of observations, which is like 20,000 or so, we needed something better and faster than this, but I will talk about it in one of the next slides. So as Andrew said, every evening and morning we observe calibrator sources, ATEM calibrator sources, such as those here, Hydra A, 3C444, Pictor A, Hercules A, or Centaurus A. I'm not showing Centaurus A picture because it would look very poor comparing to what Ben showed yesterday, so I'll hide it. Then this gets calibrated, and in the calibration solutions go to the database. In the same process, a control image is created, so we have like plenty images of calibrator fields just from the last 3 years at 150 megahertz. It would be around 2,000, few hundred from each of these calibrator fields. So if I was quite interested in looking into transients from these fields, but it haven't eventuated yet, but hopefully it will happen. And it can be actually, these fields can be monitored for transients routinely. I would like it to happen actually at some point, but if you are interested, talk to me about it. So what we wanted to upload, when we decided to upload these calibration solutions to the database, we didn't really want to upload them as raw solutions as they are here, just some compressed information like fitting. So as you can see, this here is the phase of calibration solutions for X and Y for a couple of tiles from 70 to 230 megahertz, and they are quite nice and linear over the whole band here. But what we decided is to just fit the linear function over 30 megahertz of instantaneous observing band, so we don't really fit over the whole band. And so for each tile, we have slope and intercept for both polarizations. So 4 numbers basically describe phase for each tile. And the slope basically converts to time delay or cable length. And we upload this cable length to the database, which can be directly translated into cable lengths, which then can be fixed when the array is reconfigured. Some of the tiles actually need to have cable lengths adjusted a little bit so that we have flat phases. This is not exactly what happens in all the tiles. I noticed that some of the tiles have a bit of a glitch into this picture because, as you can see, there are some offsets at some boundaries of this 30 megahertz band, and this happens typically for the long baseline tiles. I haven't really got to the bottom of this problem, but probably some people on the audience know what it is. I would suspect maybe this is related to the fiber, or maybe it is related to the ionosphere, because this specifically happens to long baseline tiles. So I think people probably know from science perspective, and they have answer for this straight away. So as I said, we fit linear function for phase, and for the amplitude of the calibration solutions, we can't obviously fit a linear function over the band. It is much more complicated. We could fit high order polynomial, but what we decided to do is to fit a linear function over a coarse channel. So this basically allows to also well fit the picket fence observations, which would be quite hard to fit with wide, like even high order polynomial. However, I was experimenting a bit with a like intermediate solution that maybe fitting polynomial, especially for continuous band observations, and then fitting and then somehow approximating it with linear function or something like this within the cross channel would be best because of the actual RFI, which if there is a lot of RFI in a single cross channel, that can make the fit quite unreliable. So the database itself is just 3 tables. So one table is, one cable calibration fits basically allows us to keep versioning of this calibration solution. So basically when we have a better set of calibration solutions, we don't really have to remove the old ones from the database. We just upload the superseding better ones and add a new version record, and that, so this way we have a history of calibration solutions in the database. The other small one is a calibration solution request. So that one is used in the situation that I talked about before, when there is missing calibration, record is inserted here, and then the script running on MWA ops computer will pick it up and calibrate, insert solutions to the database, and you should really get calibration solutions if you request the observation. So this is basically what happens if calibration solutions are missing. Give it some time, and sometimes I know it can be like more tricky, especially at some different frequency channels, and something will not go as expected. So then it will probably take more to fix the issue. But yeah, but we are trying to fix these issues if we see some uncalibrated requests waiting in this table. So the main table is calibration solution request. So every record in this table basically describes the full tile containing information about fit for both polarization. There are, as I said, delay, cable length for X and Y, intercept for X and Y. So we actually allow phase intercept to be non-zero, which is justified, especially if there are some offsets like I shown in some of the tiles. And there are arrays of these feeds per course channel for both polarization. So 24 amplitudes for X and Y, 24 for Y, and also for 24 slopes and intercepts for all for course channels. And there are additionally some quality flags, and these quality flags are basically based on the quality of the feed. So I decided to go with a number, with a ratio of number of good channels to all channels, and number of good channels. What I consider are those which have. So this ratio is calculated as a ratio of good channels to all channels, where good channels I consider those which have fit within 3 sigma from like data points within 3 sigma from the feed. So and basically this ratio I consider good quality calibration solutions to be about this ratio having about 0.6. So this is the distribution of this quality flags in the database, and you can see it doesn't go up to 1. It's because it also counts all the edge channels of all the course channels, so they are automatically flagged and excluded. So basically that's why it never will get up to 1 until we have the new correlator, where all the channels will be good, and that way it will be that straight, the calibration solutions will improve in, so to speak, way. Not really. But as you can see, there is some structure. So this structure actually comes from the fact that some frequency channels, as 150 megahertz, for example, are better than the others, and some calibrators apparently, like 3C444, give slightly better quality as well. But basically, whatever is below 0.6 is, I consider, not good solutions. And I'm not sure, but I think this flag is actually not available to the users when they download observations. But I'm not quite 100% sure about this actually. So this CASA pipeline was quite okay for calibrating observations and putting them to the database as they were collected. But once we decided to fill the database with 20,000 or so calibrations observations since 2014, it wasn't enough. So then Chris came along and created his nice distributed pipeline, so that I given him a list of calibrator observations to be processed, which was like 20,000 or so. He basically ran his system, which uses idle computers in student area, or we also used Nimbus virtual machines at POSI at some point, and it distributes it among these computers, and they are calibrated on these computers, then collected back to some central point, and then I took them and uploaded to the database. So this helped us with filling this database with historical calibration solutions. So Yeah, basically, when you download the calibration data set, you request calibrated data set, you get this data calibrated. But if you would like to actually get the solutions just bin file in Andres offering a binary format, you can either go to this web page which Andrew created, where there are all the solutions currently in the database listed, and sometimes there is a control image, although not always. Or you can use one of the wget commands on the bottom of this script, where you just provide an ops ID, and the system basically goes through the same logic that I talked about. It finds the nearest in time calibrator within 24 hours, which is maybe debatable, but and at the same observing frequency channel, and then you will download a zip file containing this calibration solution. If it's missing, then yeah, the request will be inserted, and you should get one late. You should be able to get this later. So having this sort of near real-time pipeline is also good to look at how the telescope is behaving, how it's performing, and how the calibration solutions look in time. So here is example for 16 tiles of this delay in the database over time. And as you can see, it's quite typically flat with some outliers here and there. In tiles 111 and 121, you see some glitch. So basically what happens is that receiver got rebooted there, and the clock, after reset, the clock latches with some accuracy around few nanoseconds, which translates to few meters of cable length. So basically, calibration solutions from before the glitch, the reset, of course, cannot be used after the glitch, but sometimes, as you can see, the things can return to the same state as they were before after second reboot. However, yeah, we should probably have mechanism in the data protecting from using this wrong calibration solutions. But the other thing is that if we have densely enough populated database, this shouldn't happen often, or nearly never. Okay, this information can be aggregated in one plot. So here you can see the mean delay versus antenna index going up to 128, and standard and error in this points is standard deviation of the variations of the delay over this 1 month, March 2019, for each tile. So as you can see, one of the receivers with 8 tiles here was reset, and that's why the errors are so high on this particular one. So this is a nice way of looking of what actually the tiles were doing, and this is basically going back to at least 2016. Yeah, the other situation for on compact and similar plot for compact configuration to December 2019. So other than this, as I said, many calibrator fields with possible application to look for transients. I'm interested in this myself. And also these calibration solutions, it is planned that this thing will actually run on site, on the on-site computer. It will be deployed on site. So once deployed on site, it will have direct access to the data, and it will be able to get it calibrated faster. And these calibration solutions can then be used for the new correlator, which is a fringe stopping correlator, and needs calibration solutions to be fed reasonably fresh ones. So just a few words on different, how it evolved to the SKA world. So this is the Engineering Development Array 2, which is SKA low precursor station. I think it hasn't been mentioned much in this meeting yet. So this has been deployed in the field last year, and it consists of 256 MWA dipoles, and each one of these dipoles is individually digitized. So this is basically precursor station testing the technology for SKA low. And I've been working on it for the last nearly 2 years now. And so here we actually used the experience, and we created a similar database to catalog calibration station calibration solutions from this station and other stations. So here you have an example. Okay, thank you, Randall. Of calibration solutions fits, which are now fitted over the whole band, and we allow actually intercept is forced to be either 0 or 180 degrees, just to take into account situation when the polarizations can be swapped. So similarly, we monitor it for long times, how the delays change, how stable is the system. This is important for all the documents, critical design, documentation for SK law. We can see how it performs on this aggregated plot as well. And similarly for the other station using Scala 4 antenna, which Andy was showing before. So this is AAVS2 system. And this brings me to my summary slide. And I think I just summarized that ASVO allows everyone to download calibrated MWA data and start creating images. So I hope it will be used widely in public, even outside MWA collaboration. And yeah, if you are interested in calibrator field images, talk to me. And if you are interested in possible extensions to future extensions to ASVO, talk to Greg. And thank you very much.
Perfect. Thanks very much, Martin. Let me see. There's a comment from Natasha with a suggestion about how you might be able to sort out the origin of the discontinuity on the long baseline tile. So perhaps I'll just let you two chat about that offline. Yep. Question from Sumit to everyone. Can the calibrated data files be used to image directly, or do we need to apply some other correction, e.g. self-calibration before imaging?
Yeah, I mean, this is some kind of generic basic calibration, and absolutely better ways after this are can and probably should be done if this is going to be like high quality images, self-cal. Yes, for sure.
Okay, I've got a question from Natasha, and then John's got his hand up. Natasha says, I didn't see any mention of the cross-term calibration, which is necessary for polarization. Is this something that a future version will address beyond the current scope?
Good question. Yeah, it's not implemented at the moment. That's true. And yeah, I mean, I think there is a plan to have some discussion on what are the possible extensions here. I had a quick chat about it with Greg. Whether this particular thing will be included, it's to be decided, I think. But at the moment, it's not such. And other like, for example, sky models as well could be improved, and a couple of other things as well. But yeah.
Yep. Okay, John, go ahead.
Sorry,
can
it's
we
just
say something? Yeah.
Just Greg here. Just want to jump in there and just say in general that yeah, just getting back to Sumit's question. And this next one is that, yeah, you can definitely go straight from this calibrated measurement sets or UV-Fits files straight to imaging using WS Clean or the like. And so that opens up all sorts of possibilities that of being able to extend the ASVO and extend the calibration system, but we are limited in terms of resources. So we're going to be very careful about where we apply those resources to get the most bang for buck. And so that'll be something that we'll be discussing with the management team as to where we actually apply Harry's resources, for example, over the next 2 years of his contract. Yeah, did you want to say anything else?
Yeah, so Harry's not primarily employed to do this. Harry's employed to manage the ASVO. And so the back end part of what the ASVO does is not necessarily something that Harry's primary function encompasses. And then the funding that we received to do this piece of work, which I think has been fantastic, I have to say, has been exceeded. It's finished, that project. So it's really a question, as Greg says, about prioritization and resourcing. We have a baseline set of things that we need to supply and continue to supply at a high level. If there's capacity beyond that, then we could potentially look into some of these things. But at the moment, there's not a great demand for polarization science with the MWA, and so it would certainly be a cost-benefit discussion that would have to be had. And a case would have to be leveraged that it was going to make a significant science impact, I think, to deploy those resources.
Okay, we've got 1 minute left, so we'll go to John, and then we have to go to the next session. John.
Hi, everyone. Yeah, this is really, really good. I know of one case where this won't work, and that's daytime observations during the summer. There, the heat on the cables is sufficient to completely decohere a calibration solution derived from a sunrise sunset observation. You can correct for this using temperature information. Whether the resources are worth it, I guess that's for you guys to decide.
Yeah, thanks, John. Good point. Okay, that brings to an end the technical sessions from this morning. So I'll thank again all of the speakers. It was really interesting. And I will hand over to Charlotte Sobey, who is going to be the chair of the next session. Over to you, Charlotte.
Thanks, Randall. Yes, I'm Charlotte, and I'll be chairing the next session, which is the transient science session. So, Paul, are you online and able to share your screen?
Yep. The button has disappeared for me. Here we go.
No worries. So Paul Hancock is starting us off with the transients update.
All right, just checking I shared the presentation screen and not the speaker note screen.
Yes, we can see the search bar. I don't know if you can make it.
No, I don't know how to do that. Sorry.
Okay. All right. You're all good then.
Okay, so
warning, Paul.
all right, cheers. Okay, folks, so I'm going to give an update on some of the transients group activities and a bit of an overview. So just a little bit about the transients group. It's actually the variable and slow transients group. So we're also interested in anything that is changing in the night sky slowly, variable sources, not just what you would normally think as impulsive transients. So in terms of the group structure, I'm the science lead for the group. If you want to join and be a member of the transients group, just like the sources we study, the membership varies with time. There's no forms you have to fill out to join. You can just turn up to meetings. You can join the mailing list, which I've indicated here, and you can read all of our activities on the wiki in terms of meeting notes and things like that. So feel free to join and participate as that is useful to you. I will say that currently the majority of the people who attend the meetings are all at Curtin. And so I suspect that there is more transient and variable science being done at places apart from Curtin. So if you are somebody who's doing that work, please feel free to join the email list and come along to the telecons. At the moment, we're having telecons only quarterly, and the timing is subject to availability of anybody who wishes to attend. So don't feel like you're going to get locked into a 3 a.m. your time meeting schedule by joining the transients group. So we'll leave that, the exact timing to be open. So that's about the transients group. And I want to give a couple of updates about some of the projects that are going on within the transients group. So the first that I want to talk about is using the MWA in a way that it was completely not designed for, and that is for tracking space debris. So there's actually two different approaches that you can use the MWA to detect space debris, and I'm going to talk here about what we're calling the non-coherent approach. So in this approach, what we do is the general workflow is to create very high time and frequency resolution images from the correlated data. So I say high time and frequency, I mean sort of 2 seconds time resolution and 10 kilohertz frequency resolution, because that's sort of the highest frequency resolution we can get out of the correlated data, which is in the archive. So we create images on that cadence. And as you can see in the little animated GIF there, that sometimes we get very bright events which streak through the images. And you can say, okay, that's obviously not a planet, it's not a star, this is actually a piece of space debris. And this one is actually one of the dreaded Starlink satellites transiting through. Now, our normal detection method is actually to take images that are adjacent in time and subtract them from each other, so that all of the non-moving, mostly astrophysical sources just get completely removed. Any extended emission from the galaxy, anything like that, gets removed. And what you're left with is only the things that are moving quickly through the image, which are objects in low Earth orbit, also airplanes, and occasionally meteors through the atmosphere. So we have Steve Prabhu's PhD project is primarily focused on the detection of objects in low Earth orbit. Not only are we able to detect the reflected emission, so what's happening here is that we've got the MWA as a receiving station. We have other FM broadcasters around Australia broadcasting radio to people's houses, but also some of that leaking into space, reflecting off debris, and then being reflected back down to the MWA. So we're using the MWA as a bistatic passive radar system. So we see all of these objects through their reflected radio emission, but there are occasionally some CubeSats that seem to have some out-of-band transmission, such as what you're seeing on the bottom right here, where we've got a time versus frequency plot. And you can see that there's the UCube1 CubeSat has this broadband emission, which is not actually what they're supposed to be doing. So there's another way of tracking objects, but also monitoring people's adherence to various agreements about what you can and can't do in low Earth orbit. So we have an entire pipeline set up that will more or less automatically calibrate and process a whole range of data. We've got 20 hours of data in our initial blind survey, where we're trying to determine what the limits of detectability are. So on the top left plot here, we've got the vertical axis being the range, so the line of sight range to objects in orbit, and the horizontal axis is the radar cross-section, so essentially the reflecting area. The black dots here are all of the known catalogued objects, and the two colors here represent our different cuts for detectability, and the most purple region in the bottom right is the area where we think we should be able to detect all of these objects if the RCS is correct. And you can see these colored dots here. These are all of the objects that we've been able to detect in this 20-hour blind survey. So I think it represents about a third to a half of all of the objects in that area there. So if you want more information about that, you can either contact Steve Prabhu, or you can see one of the two papers that are on the archive. The first one published and the second one submitted and under review at the moment. So the next bit of work is using the VO event trigger system, which we developed for the MWA and published last year. And so this project is to follow up short GRBs. So the idea here being that we want to look for the earliest time emission that is coming from short GRBs, not the sort of days to weeks radio follow-up from some kind of fireball, but what we're looking for is something which is like a fast radio pulse, as not necessarily a fast radio burst, an FRB, but something that's connected to the GRB. And this particular GRB is one of the ones that we've put a lot of our early analysis work into, because it's a swift triggered GRB, which means we know the position to within an arc second or so easily within a single synthesized beam of the MWA. The X-ray light curve shows a plateau, which is consistent with having a stable magnetar being formed. And so either the formation or eventual collapse of this magnetar is predicted to be able to produce a radio pulse. And it's that pulse that we're looking for. So again, this is using correlated imaged observations. The light curves that you can see in the middle here are taken at a cadence of either 2 minutes, which is our individual observation cadence, or as short as half a second, which is the time resolution that we have for these observations. So what we've been trying to do, given that we're looking for a very short pulse that could be dispersed over time, we have some code from Marchin, which is able to take all of the images at different time and frequencies and essentially form up a waterfall plot of frequency versus time, and then do a dispersion measure search through those data. So this is similar to what you would do when looking for FRBs, except the core data is actually from imaging data rather than voltages. We do have plans to use voltage data in the future. So recently we've enabled the VO event triggering system to be able to capture VCS data. We have all of that coded up and in place, and once the MWA is back online and accepting triggers again, we'll hopefully get some VCS triggers as well that we can process using a more, let's say, traditional FRB single pulse search type thing. So this is the paper that was sent around a little while ago for collaboration review, but there's additional work going on, a lot of other GRBs, which Jun Qian is doing as part of his PhD project. So more on the triggering side of things, for a long time, the MWA has been triggering on Antares neutrino events. This is essentially all of the alerts that were sent to the MWA. It is not that many, over 2.5 years. And unfortunately, a lot of these events were kind of at the wrong time or at the wrong place. So the MWA wasn't able to trigger. This triggering was all done using I think like a GCN packet system. I don't really understand what it does. The problem is not really anybody else understands how that triggering system works. So the goal at the moment is to be able to create a VO event filter that will be able to get the MWA to respond to neutrino events. And once we've got that in place, we can use a lot of the automated data reduction and analysis software that we've developed for things like GRBs and for transients and variables work, and then just apply that to the Antares triggers that we will hopefully receive in the next semester with the MWA. So the last piece of work that I wanted to talk about is search for transients, and this is more of an exploration of a methodology. So this is a project that honours student Tyrone Doherty is working on. And broadly speaking, there's sort of just maybe 2 approaches to finding transients and variables in a set of observations. One approach is to image all the observations, do source finding, create catalogs, track light curves through the catalogs, and look for things that appear and disappear. That's all nice, but takes a lot of effort, a lot of processing. There's a lot of false positives in that process. Another approach is to actually just directly compare your current image to a reference image and do an image differencing. Now, in optical, this works quite well because they've got fairly stable PSF. Obviously, in radio, we don't have such a stable PSF, and so most of the differencing, most of what you see in a difference image is just differences in PSFs, and you get a horrible array of false positives there. However, if you were to have 2 observations that have the same UV coverage and the same flagging, then you would expect to have no difference in the PSF of that image. And so you should expect the subtraction of those two images to go extremely well. And so that's something that we've been exploring a little bit, but then we realized that instead of actually subtracting the images, if you've already got the visibilities matched in terms of their UV coverage, why don't you just subtract the visibilities directly? And so that's what we're exploring here. And the advantage is that you only need to form the images once. You still need to calibrate the two observations separately, but you only need to image once. And what's being demonstrated here is on the left-hand side, this is a single image, which has been cleaned. And so it's good, but not amazing, what you can see here. And on the right-hand side is the difference between two images where we've differenced the visibilities, but we have not cleaned. There is no cleaning happening on the right-hand image. And so you can see that most of the sky is empty because the static, not changing sources have just subtracted away perfectly. There are a couple of weird little butterflies left over due to maybe slight shifts in the ionosphere where it's putting the emission in slightly different places. But you can already see that there's a huge benefit to doing this visibility differencing. So the initial testing is very encouraging. Thankfully, the MWA has an enormous archive that Greg wants to delete. But the huge archive means that there's lots of opportunity to find observations that have the same LST, the same frequency, the same pointing center. And so we can find lots of these LST matched pairs of observations. And in fact, the GLEAM survey is a very rich source of such LST matched observations because of the way that it was scheduled. So I just wanted to wrap up by saying that you should join the transients group. We have lots of tasty little cookies that you might enjoy. So apart from all of the awesome science that we want to do, we have a lot of expertise in developing and using the automated VO event triggering system. We have imaging processing pipelines where you can get very easily and fairly quickly very good, I would say, science quality, depending on your science case, images. We have analysis code for doing like a bulk processing of the image reduction and creating light curves and things like that. And we also have many honours and PhD projects available. So I'll leave the information up here for how to join the mailing list and how to find more information on the wiki. Thank you.
Thanks, Paul. That's great. We have a couple of questions in the chat. And Nicole has a hand up, so I'll let Nicole ask a question first.
I'll keep it brief. So Mike Walensky has also used similar differencing techniques to find digital television. And I was wondering if maybe there's a bit of overlap there. We don't want to reproduce efforts, obviously. So maybe, I don't know, has Steve seen any digital television or TV off of bush planes or something like that?
We haven't looked at those frequencies yet. So at the moment, we've been looking at the FM band in Australia, which is sort of 80 to 100 megahertz. But we have flagged some of the higher frequency bands, in particular digital television, as you mentioned, as places that we can look next. And part of the motivation is because of Mike Walensky's work. So that is something that we plan to look at in the future.
Great, yeah. Definitely keep in touch with Mike because he probably has some observation IDs he can just hand you that would be interesting to look at.
Yeah, excellent. Yep, that'd be good. Yeah, in fact, that's kind of how we started with this project, is that Xiang was looking for meteors in MWA data for her PhD project. And she found a bunch of satellites and said, oh, that's interesting and cool, but I don't have time for that right now. And so the initial work that we did with Steve's PhD was actually to use the OBS IDs that Xiang had already identified as containing satellites. So it'd be really cool to do the same sort of thing with Mike Walensky's observations as well, given that we know that things exist there and that an independent analysis has revealed that that should be detectable.
Great, thanks for that. We also have a question from Randall, who asks, imaging difference visibilities is the same as differencing dirty images. Is there an additional value in making dirty images?
Additional value. So, I mean, the advantage of doing the difference visibilities first is that you only need to spend time making the images once. The downside is that if you want to make image plane corrections to your images, so if you wanted to correct for the ionosphere, we can't currently do that in the visibilities. And we would, if we wanted to apply something such as Fitzwarp to do that sort of image domain correction, we couldn't do that in the visibility. So if we wanted to go down that path, then there would be an advantage to doing the differencing in the image plane rather than in the visibility plane.
That's great, thanks. Are there any, I think Zhang also just posted a comment that also dirty images can help checking if the difference in the source is actually scintillation.
Yes. Yeah, so when you're looking at an empty visibility difference image and it's got one thing in it, you don't really have any context as to what's going on there. So looking at the individual non-differenced images does help give you that context as to whether it's a source that's scintillating or whether it's a transient that wasn't present earlier. So, yep.
That's great. Thanks very much, Paul. I will applaud on behalf of all the participants.
Thank you.
And we'll move on to Alex's talk. So, Alex, do you mind sharing your screen?
Sure.
Please.
Can everyone see that?
It looks good to me.
Awesome.
Yeah, so I'll just introduce you. We have Alex Williamson, who's going to tell us about cosmic rays with the MWA. Take it away, Alex.
Hi all. So I'm just going to be giving a brief update on my search for cosmic rays with the MWA over the past couple of years. So to start off, just quick, what are cosmic rays? They're high energy particles that hit our atmosphere and explode. The thing that I'm most interested in is the radio emission that they produce when this happens. And we should be able to detect them at the MWA using in radio. And that's pretty much what I'm going to be talking about today. So first of all, why do we care? We don't really know generally where they come from. There's quite a few candidates. But the main issue is that charged cosmic rays are deflected in magnetic fields. And so we see them come from pretty much everywhere at once. Now, in terms of the energies, the cosmic ray energies that we expect and how many we expect, this is just a spectrum of cosmic rays, which relates the energy on the x-axis to the flux on the y-axis. There's two features. You have the knee and the ankle. Generally, it's shown that below the knee, you can expect galactic cosmic rays. Above the ankle, you should expect extragalactic cosmic rays. And in between the two, you should expect a mixture of both. Now, the important bit about this is it predicts what kind of detection rates we should expect at the different energies. So if you're looking at about 10 to the 15 electron volts, you're looking at roughly a detection every 30 seconds, provided you've got the sensitivity to detect those cosmic rays. At about 10 to the 16 electron volts, that goes up to 1 detection per hour. And about 10 to the 17, that goes up to about 1 detection per week. So the detection rates can ramp down quite drastically. And so mostly what I'm looking for is cosmic rays in the sort of 10 to the 16, 10 to the 17 electron volt mark. Now, what would we expect in terms of the signals from the cosmic rays? Now, I'm using the VCS mode of the MWA, so I'm looking at raw voltages. And this particular plot is just what we would expect based on simulations of cosmic rays. So in this case, we've got a 10 to the 16 electron volt cosmic ray that comes down from zenith. And at the tile, what we would expect is a signal that a really sharp, short signal that looks like this, around about 10 nanoseconds wide. Now, for those of you who know about what time resolution we get out of the VCS, we're looking at about 100 microsecond time resolution. So that's definitely not going to do for my project at all. So a good portion of my work has been to invert the PFBs. Now, Sammy McSweeney has done a lot of work on the fine inverse PFB, so I'm not going to talk about that because my focus has been on inverting the coarse inverse PFB. Now, the main issue with inverting the coarse PFB is that in the forward process, you have a 1.5 nanosecond time resolution. Once it goes through the coarse PFB that channelizes the signals into 1.28 megahertz frequency channels, only 24 of the 256 channels are passed on down the chain. So that's less than 10% of the information that I have to reconstruct the time series. So from a lot of work, I've been able to get it down to about 16.27 nanosecond time resolution with no frequency information. So just as a quick idea of what a polyphase filter bank or PFB does. So this is my best representation of it. So if you take your input voltage stream, you can fold it up into multiple branches. You Fourier transform along one axis, and you convolve with a filter on the other axis, and you get output that has frequency and time information with the time resolution reduced based on the number of frequency channels that you've split your signal up. The inverse PFB is very similar. So if you take the output of the PFB, you invert the frequency along the frequency axis. You choose a filter. Now this is the important bit because the choice of filter determines how good your reconstruction is. And you convolve that to get a set of branched voltages, which you can then unfold to get your voltage stream. There's multiple ways to do an inverse PFB, and it depends on whether your PFB is critically sampled or oversampled. But this is the best way that I can represent it. And there's obviously a few extra details in there that can go into that. So what does this look like in practice? So if we take a standard impulse and we pass it through my theoretical PFB, you get a channelized signal. So this is all 256 channels, and you should just be able to see one single thing. I've not introduced any bandpass or anything like this. This is purely theoretical. And you invert that using my inverse PFB code, you get something that looks pretty similar to the original signal. Now, what happens if you only take 24 channels of that? Now, it doesn't matter which choice of 24 channels you choose here. In theory, in practice, there's RFI and all sorts of other stuff at the MWA. But if you choose 24 channels and you do the inversion, you get a bit of rippling. And that's not too much of a worry because most of that ripple is underneath the noise floor at the MWA. One caveat to this is the location of the impulse in the voltage in the voltage block can also affect the amount of artifacts that you see. So if I move that input signal 256 samples to the right before the PFB, you get a few echoes. Now, this is also not too bad because that's very, very close to the noise floor. And I'm not really worried about the shape of the signals because we're just measuring a cosmic ray would essentially be one sample in my voltage stream. So it's not too much of an issue. So in terms of the data collection and processing, I've currently got 20 minutes of test data, 4 hours of fully processed data, 2 of which that I still need to look through the results for, and 20 hours still to be observed / processed, somewhere in between those two. Now in total, this is about 600 terabytes of data. That's a massive amount of data. And so I'm not going to be keeping any of the raw data for this. I expect probably 1 to 2 signals per hour at maximum in terms of cosmic rays, probably a bit more in terms of RFI. And I'm only going to be saving about a microsecond per signal, which is about a few hundred megabytes. So not to worry about all this data. All the raw data is going to be deleted at some point in the future. So the first bit of experimenting that I did was my barbecue lighter experiment. So for those of you who don't know, if you click certain barbecue lighters, they produce nice short, sharp pulses of RFI. And so during one of the maintenance periods, the ops team helped get some data. So one of them walked around the MWA with a barbecue lighter, clicking it, and we recorded the voltages at the same time. So what does that look like in the data? So from one of the tiles, we see something that looks like this. This is really bright, obviously, because they were standing right next to the tile. And we can zoom in on this signal and zoom in again and again. Now this is 15 microseconds across. Now what you should notice is that one short sharp pulse, which is just seen in the raw VCS without inverting the PFBs, has certain amount of structure within it. Now I'm going to leave that open as to why this structure. That's not my problem right now. What is interesting is this 15 microseconds is less than 1 sample in the standard VCS. So you probably wouldn't see any of the structure. You wouldn't see any of the structure at all. One of the cool things that we can now do is, because we've got that high time resolution, we can now take the arrival times of those signals at each of the antenna and reconstruct a source location to the best of our abilities. So this plot was made by taking a number of those gaslighter pulses within a short period of time and reconstructing them. And you get about a 5 meter scatter, and looking at the light travel time for light travel distance for about 16.7 nanoseconds is about 4.8 meters. So that's roughly consistent with what I would expect. Now, on to more recent results. Now, if we had the MWA meeting at the original date, we probably wouldn't see this stuff, because I've only looked at this in the past week or so. So I've detected a signal. Now, for those of you who don't know, that's this very bright signal at this point here on the right. And we can zoom into that quite far and zoom in again. And you can see that this signal is very, very short and sharp. In fact, it's pretty much at my time resolution. Now, why don't I think this is a cosmic ray rather than RFI? Because it pretty much triggered across the entire array. And for a cosmic ray, we don't expect, we expect probably about 400 meters east-west width, or 800 meters north-south at the maximum. The other red flag for this one is that we detected probably 1 or 2 every 30 for a period of about 30 seconds. So it was pretty bright for 30 seconds, and so I don't think it's RFI. I don't think it's cosmic ray. I'm pretty sure it's RFI. Now, is it random noise? Well, you can fit a plane to it, and you probably can't see that fit all too well, but the plane fits relatively well. There's quite a bit of scatter, which we're still investigating, but in general, you can basically say that this signal came from roughly the northern direction, pretty much close to zenith. So in terms of the environments of the MWA, a few of you have seen this slide before. So for a Six Sigma, this is one of the tests that I initially did at the site. So for Six Sigma, you should expect about 1 in 500 million random noise triggers. We've got about 300 million samples per tile, both polarizations for 8 seconds. So we should expect about 30 false detections from Gaussian noise for 48 tiles. And that's roughly what we expect here. I think there's about 35 points on that plot. So each of those points on that plot is a sample above 6 sigma. And so we can it's safe to say that for instance, at the time resolution that I'm looking at, the RFI environment is relatively quiet. And apart from 1 or 2 very pulsy sources. Okay, so I'm going to wrap up there. It was just a quick glance at what I've been up to lately. We can detect signals on nanosecond timescales by inverting the MWA PFBs. I've measured some RFI that probably won't show up in normal MWA data unless it's incredibly bright. And from experiment, the MWA site has been incredibly quiet when it comes to RFI on the timescales that I'm looking at. On top of that, I still have a ton of data to search through, and that's probably all these results will probably change within the next month or so. And that's where I'm going to leave it. So I'll leave it open for questions now.
That's great. Thanks very much, Alex. We have one question from Sumit already that says he's not getting why you consider 24 channels out of 128 for cosmic ray detection, but I'm guessing that refers to the coarse channels.
Yeah, so that with the MWA process, you only get 24 coarse channels, and that's to do with transfer rates and limits on how much data we can record at one time.
Okay, we also have a question from Aman. How do you choose the filter to invert the PFB?
That is, at the moment, it's been quite a lot of experimenting. I think Sammy might touch on it in his talk for the fine PFB inversion. But in my case, it was more experimentation to find the best filter, and I just picked whatever worked best.
I might just comment on that since you bring it up, since I won't be talking about it specifically in my talk. But you can do various optimization procedures. I can only speak for the fine PFB inversion that I've been working on. And we've finally settled on a least squares optimization. But there are other cheaper, easier to find ones that don't do as good a job, but which are also perfectly adequate. So I can't speak to what Alex has found, but that's what we've got.
Yeah, so I'm not looking at a precise filter at this point in time. I don't have the time left in my PhD to investigate that much further. But what I've got at the moment does a pretty good job at reconstructing specifically the arrival times of the pulses. So that's what I'm looking for.
Thanks. There's also one last question from Martin about your nanosecond RFI event. Did you check if there is ISS or other satellites passing overhead?
I haven't looked. Pretty much that data came in. Well, I looked at that data over the last couple of weeks, so I haven't had much time to narrow down where the source, what produced the RFI, but I'm looking into it at the same time as processing all the other data.
That's great. Thanks very much, Alex. I also applaud on behalf of all the participants. And I think we'll leave it there and break for lunch. Is there any announcements or anything that people would like to make before we break for lunch?
No, not really. I mean, the only thing I can think of I should say now is, yeah, speakers for the next session, make sure you're back on time and you're prepared. Yeah, that's all I've got to say.
That's great. Okay, so I think we'll be back in almost 1 hour. So I'll see you all back soon. Thanks, everyone. Okay, hi everyone. We're just going to get started with the afternoon session, back with the transients. Xishan, do you mind sharing your screen, please?
Okay, wait a second.
Okay, thanks.
Okay, can you see my screen?
I can't see anything at the moment.
Can you see it now?
Yes, that looks good to me.
Okay.
So our first talk of the session is from Xishan Xu, who is going to tell us about the Shell transient pipeline. Thanks.
Okay, thank you. Hello, everyone. My name is Xu Zhijun, and I'm from Shell. Today, I will introduce the Shell transient pipeline step. This is the GitHub page of the step, and thanks for my colleague Guo Shaoguang to help me with the GitHub and contribute to the interface of the step. Step is developed on China SK prototype. And lists some of the performance compared to the MWA recent update computer cluster. I can see it's still, you can see it's still competitive in SSD storage and main memories. And we are also having the phase 2 update recently. You can also see it in later Professor Zhang's talk. She will add a bit more details. This is the system diagram of step, including correlator, imaging pipeline, FRB search pipeline, snapshots, and AI applications. First is the correlator diagram. Someone may saw some of the following slides because I sent it to Greg to show it on the Python meeting last year in Curtin because the meeting is delayed and I'm on my way back to Shanghai. Anyway, I will briefly introduce it. And so the correlator is designed to get the benchmarks for different Python library. First, I test the result with Ian's MWAX correlator result to make sure the program is correct. In the benchmark, I test the Python's CPU library, NumPy, and the AI library PyTorch, which can run on CPU or GPU. And the benchmark only tested on the GPU. And another Python GPU library, CuPy, which can be regarded as a GPU version of NumPy. We also test the library on different platforms. So this is the final benchmark. I will just show the conclusions. PyTorch has the advantage of high utilization of GPU memory and high performance of heavy data, and also can easily implement AI algorithms. CuPy has the advantage of more NumPy likely and the support of the complex value algorithm. This is another benchmark made by my colleague Liu Lei. He made a benchmark to show the performance of PyTorch and CuPy. The CuPy performance is quite well The PyTorch in general is not performed well, but it lost mainly in the decode, which is normally we don't use PyTorch to do that. And in compute, PyTorch performs quite well, even in some cases better than CUDA. So after Correlator is the imaging pipeline. This work is done by my colleague Lao Baoqiang. This is the result of our recent observation of SGR 1935 using MWA, which thanks to the MWA director and the operation team. The result is no, we didn't find any radio emission. It was detected about like 5 sigma, and we will do more research on the supernova remnants. And Lao Baoqiang also working on AI applications like radio galaxy classifications and source findings. Then let's first see the snapshots. Snapshot can plot all the data in given DM. So if we already know DM, it can generate a PDF file contains all the result images. As you can see, the bottom is the, so the bottom is the raw data, and the middle one is the dispersion data, which also have been done with IFI removing, channel ignoring, boxcar, etc. This is the result of the MWA correlator. Correlator filter bank file. And this is the MWA VCS PSR fit file result. Here is the result of the ASCAP public FRB observations. With the given DM, the snapshot can easily find all the FRBs in all 19 observations. In total beings, it's 36 beings. And more than 3,000 seconds per being data. It takes less than 3,000 seconds with single GPU. It's about 40 times faster than the data time. Okay, snapshot program is for given DM, but if we don't know the DM, we will use the searching pipeline. Which is almost the same algorithm, but with maybe thousands of different DMs to run. And here's some result we find using searching pipeline. This is the PAX FRBs, and ASCAP, the same FRBs, the TMA telescope pulsar result, and WMA pulsar results. For the searching pipeline, the main problem is there's too many candidates. It's really too many. You spend too many times to see the results. And for a wide range of DMs, it will spend lots of time in the searching. And it needs to carefully remove the IFI. Otherwise, you will have a lot of useless results. So we are thinking about using AIs to detect FRBs. At first, we generate about 4,000, 4,000 simulated FRB images, which the FRB signal is based on the real FRB observations. And the same number of the non-FRB images. You can see it here. This is the FRB images, and this is the blank. It's the non-FRB images. And we also implement, in example, we used pre-trained ResNet, which, by the way, is quite easy to use by using the PyTorch. And the result too good. In the first training epoch, the accuracy is already almost 98%. And after several epochs, accuracy is 99.7. So it seems too good to be true. So we add some same number of IFI this page, and the IFI is roughly just a negative DM of FRBs. So it's easy to implement. So we find the result even better because I guess it's because of the training set numbers increase. So, okay, let's add some weak FRBs, but the result is still too good. And we have a close look at the weak FRBs. And we find it's some strange weak lines which will not happen in the real data. So we just replace this part to noise, and finally the accuracy is down to 90%, and in 97 in the best. So now we have the trained modules. It's time to bring it to the real world. So I plot about 800 FRB. This is from FRB 1704-16 to test. This is the real data. The first run is failed. I examined the image and find the images. It's upside down. So thanks for helping me to find the bugs. Okay, we fixed the bugs. Then the second run, it still failed. I checked the image again and find out the FRB has only half part in the image, which in training I was set to the full part in the image. So instead of to retrain the half part FRBs, I just set an offset to the test image to make it show the full part. And in the third run, it's finally success. It result 6 positive, which 3 is right. And I checked the other 3 wrong results, and I'm thinking about, let me go back. Thinking about because we added too many weak signals, so any case they find something in this part, they will recognize it to the with FRB. So later we will fix that. Okay. So we also because I was thinking about to release some data and the papers, but the time is too limited because this I just got some of the results. So anyway, I will work on it, and the data will release in the GitHub page of STEP. And we also have some other tools like SkyMag and Gene, Generate Figure, Pi, and others. So the conclusions, the PyTorch is quite powerful tools. And I didn't mention about custom CUDA libraries. It can make it's more powerful. It's maybe can just compare to the CUDA programs. And it's quite easy to implement the AI applications. Another machine learning FRB dataset can train the AI to detect FRBs in raw data. So we are not talking about the searching it in the candidates. In the raw data, it means you do not have to do the hard work about IFI removings like that. But we still have lots of things to do. Like right now, I only add one FRB signals in the signal lab. So next, I will add more FRBs and maybe add more IFI offset and extra in the training set. And then I will prepare the paper and release the data set. And also we will release the tools to generate the data set and try to build some data set for Tianma, Parks, FAST, or even MWA data. And we are thinking about to data challenge, which we can test the state-of-art AIs. And we will also add more AI applications in the image pipeline, like the radio galaxy classifications and the source findings. And we will release the data set and the future works in the STEP GitHub. Okay, thank you.
That's great. Thanks very much, Xizhen. Are there any questions, either in the chat or feel free to raise your hand? Is there a question? Maybe I can ask one. What's the processing time for your toolkit?
Sorry, for which one?
For something like the FRB search, do you know like how long it will take to process like a standard data set?
You mean the AI or other program?
Yeah, with the AI.
The AI is quite fast because compared to the training, it can like maybe 1 minute for 10,000 images. So yeah, it's quite fast. So yeah, I'm also it's very nice questions, because I'm also thinking about implement the AI algorithm in the real systems to detect the FRBs in the real time. Yeah.
That's great. It sounds very promising. I will applaud on behalf of all of the participants. Thanks very much again.
Okay, thank you.
Thank you. So now we'll move on to the BCS science session, and Ramesh is going to start us off. Can you share your screen, Ramesh?
Sorry, sir. Okay. All right. Let me share my screen. Okay. So, sorry, I am in the wrong place. Share screen. Can you see it? Okay.
Yeah, if you could just start the presentation, I think that would make it full screen. Yeah, there you go. Thanks. So now we'll have a BCS update from Ramesh.
Good afternoon, everyone, or good morning or good evening, whatever might apply to you. So for those who don't know me, I'm Ramesh Bhatt. I'm based here at Curtin and I do pulsars. So I'm going to give you a quick update on the VCS side of MWA science. So VCS was mentioned quite a few times at this meeting, and it's the voltage capture system. So the MWA's functionality to record fine channelized voltage data. We can do it from every single tile. And if you want to do pulsars, and because MWA doesn't have a dedicated pulsar backend, you have to bring all this data to POSI and do all your calibration and tide array processing. And that is how we detect pulsars.
So that is many terabytes of data collection, and over a typical semester, we collect something like a couple of petabytes, and a fairly non-traditional and a really data-intensive science, and it comes with its fair share of challenges and a good bunch of pros and cons. None of those has stopped us from going forward, and over the past few years, and we have learned to work with those constraints and staying within the boundary conditions, and notwithstanding the limitations, we have learned the art of how to work with it and produce a whole bunch of good science, primarily on pulsars, from topics ranging from emission mechanisms to ISM propagation, from millisecond pulsars to transient pulsars. We also have been doing quite a good job of documenting a whole range of capabilities we develop. So almost 18 publications have come from VCS over the past few years, and almost a third of them have come from the past year or so. So past year also has been quite exciting because of that's the, our first year of our first cohort of students graduating. And this is one activity that has relied quite heavily on the graduate students and using them as like a workhorses. Pretty much every single student has been like scoped or developed around developing an important capability and getting them to do the very first science. And they all have been quite enjoying that. So that's the model that we are tending to follow. So Bradley Myers and now UBC postdoc and graduated already. And a few months ago, Sammy graduated formally, and exam process nearly concluding for Menya. And at this point, we are talking about something like a matter of just weeks. So with those two important boxes ticked, I feel comfortable to say that we have reached that first important milestone for MWA Pulsar Science. Now it is time to start the second innings, and which is what has been happening over the 6 months or so. There's a whole bunch of ongoing projects and new activities, and you will hear quite a few talks on Pulsar Science from Sammy, Dilpreet, and Shongli after me. And most of my time I will spend in giving you an update of a smart pulsar survey, which has been consuming a lot of our time and energy in the past semester or so. But I would also like to mention that BCS is going to be beginning to be exploited quite nicely for a whole range of non-pulsar science, like you heard from Alex about cosmic ray detections. And there are multiple active projects on the telescope at the moment, and they're revolving around FRB, GRBs, and GW events detectants. Hopefully you will hear more about that in the next meeting. So what is Smart Pulsar Survey? It's an all-sky voltage capture pulsar survey that nicely leverages MWA's unique strengths and some really good advantages. It has a very large field of view, and we have voltage capture system. So when it comes to like collecting data that is good for pulsar searches, we can just cover like several hundred square degree, which is like a couple of orders of magnitude faster in terms of survey speed compared to any other telescopes in the world. And because the MWA has this so-called compact configuration, which is a very pulsar-friendly configuration when it comes to searches, that gives us like something like a couple of orders of magnitude processing efficiency in terms of beam forming or tiling the sky, which is like a traditional way of doing pulsar searches. And that's why it is rapid and so smart, but at the same time, it doesn't undermine the real complexity in terms of processing, because we are talking about processing every single VCS observations into many thousands of beams. Each one of those beams has to be processed for like many thousands of DM trials. So there is a lot of computation involved. But from a science point of view, it is essentially a low frequency version of the very successful Parkes hit-run survey project. So as and when the compact array comes available, we do like this survey in stages. And over the past couple of years, we have had like 3 big campaigns. And at this point, we have covered the sky something like 60% by this time, and another 40% to go. And so to give you like a bit of an idea about the scope of this project, we are talking about something like 3 petabytes of data collection by the completion of the survey, which has to be processed to generate more than 500,000 beams. And even to do like a very first pass non-pulsar search, we are talking about something like 7 million core hours. So it's a very, very interesting computationally challenging problem. So we have 2 main major pipelines, and that is churning through this data. And the first one is what we call like a quick look pipeline, but it's far from quick, or it's quite an oversimplified term. So basically what happens that every single observation from SMART goes through this Keegan's pipeline, where it gets takes the calibrated calibration for the observation and forms a beam on every single non-pulsar in that observation, so that we can check the sensitivity that we are reaching, and we can detect the non-pulsars at low frequencies. This is also part of Keegan's master's research project. And the second one, which is the real search pipeline, which we run on OSTAR, because our pipeline runs several times faster on OSTAR GPUs. The front end of the pipeline is like the multi-pixel beamformer, which is a capability to produce dozens of beams, tide array beams at once, and that is the software that Nick Swainson has essentially developed. Nick is like 13 PhD candidate, and who has been doing much of the grounding together the search pipeline. But even to do a first pass shallow search, and it's quite computationally expensive. So we get something like 500,000 core hours on OSTAR every year at this point. So we are basically doing something called like a first pass shallow search, reaching something like a 30% of the array sensitivity. And they're basically like chasing a low hanging fruits at this point. So where do we stand? So here's pretty much every single observation has been processed and quality checked through these pipelines. And the red dots there are like detections of non-pulsars, and that basically gives us the confidence that the data are all like in a good order. And this is something which you really want to do, because if something is not quite right, and we want to go back and re-observe it when the compact array is still available. So just like every other survey, we just relies on the fullest coverage for success, and we are hoping to complete this survey when the phase 2 and the VCS is still available. But at this point, that we can only afford to do like a search to a fractional sensitivity. And those shaded observations are essentially the ones which have been searched through, which is literally like a 5% of the data that have been searched to 30% of the sensitivity. And half of them have generated like several thousands of candidates, and which has been sifted through Nick's eagle eyes. And there goes the green dot. That is our first new pulsar. So how does it look to pulsar astronomer sites? So in case you haven't seen one of these plots, this is one of the plots that comes from our search pipeline. This is a whole bunch of diagnostic plots that shows the pulsar profile and the signal versus time and frequency, and the pulsars, the signal strength in terms of dispersion measure and periodicity search and so on. So essentially it was seen as like a 12 sigma candidate in the initial processing. And then we go back and fetch those 40 terabytes of data and do a full tide array beam. And then there it is, so we can comfortably confirm using our own observation that it's a real pulsar or not. So this is just a different representation of the same thing. And the top left panel is essentially the localization, the period and dispersion measure space. And the middle panels are signal strength versus running in time and the frequency. And the bottom panel is a zoomed version of the pulse profile. So in terms of basic characteristics, it looks like a fairly ordinary pulsars with a DM of 23 and a period of about a second. But it's our first pulsar, so in a way it's really special. But let me tell you a few really special things that we get to do, or something which is really special for the MWA pulsar survey. And one of them is like our ability to determine its position. So typically when you have a pulsar candidate, with every other telescope, you go back to the telescope and burn some 5 to 10 times more time to confirm that pulsar, and do the gridding by doing one by one, and then get to like a few arc minutes kind of a position. So because MWA has like 3 different configurations, and we record voltages, so you can go back and flexibly reprocess that and make multiple layers of dense grids. And we can go back from 20 arc minutes kind of a position to sub arc minute position by using nicely, this archival data and the survey data combination. And in this case, it really nicely worked out, because this pulsar happened to be in the field where one of Sammy's favorite pulsar is. So we had the archival data from both phase 1 and the phase 2 extended. So we have a sub-arc minute level position, and we can do that without requesting even a single byte of extra data before we go back to Melanie and request time for its timing follow-up. So other nice thing we can do, so for whatever it is worth, we can reprocess the data, calibrate it for polarimetry, and learn a few things about the pulsar itself. Things like rotation measure comes as like a bonus, whatever it is worth. And you can get this position angle versus phase, which we can fit for what is called a rotating vector model to determine pulsar's geometry. So practically, no pulsar surveys are generally done in the full polarimetric mode, but we can get it from our own survey data. So at this point, we cannot really uniquely constrain the pulsar geometry. So you essentially need these two angles. One is the inclination angle, which is between magnetic and the spin axis, and the other is the angle between the spin axis and the line of sight. So we are trying to improve our signal detection here, so we can do like a better modeling. So we had, thanks to archival data, we have been able to detect that multiple times, and just like most other pulsars in MWA band, this pulsar also has sometimes a good day and sometimes a bad day. So bottom line, it varies quite a lot, and which is not really surprising given the DM of the pulsar and low frequencies of the MWA. But those data are still not really suitable for doing what is called a phase connection. So this is like a specially designed observations that where we are trying to determine the pulsar spin and astrometric parameters. And that's what we are doing at this point using a dedicated DDT observations. And this caused some very interesting challenges like, keeping the pulsar in the beam and sun out, and working within the constraints of VCS limitations to do like multiple observations that you need to efficiently phase connect. And Andrew, who is sitting here, has been very patiently working with us, and while we struggle through these constraints and trying to come up with an interesting strategy that will work through this. And these are the observations that are currently in progress, and we are still working through it. But it is more or less clear that this is a relatively faint target, something of the order of a few millijansky. We haven't seen that in the Stokes imaging or Stokes V imaging with the MWA. So basically, it is tending towards the possibility that it could be near the top end of the so-called low luminosity class of pulsars. A class of pulsars for which only very few objects are known at this point of time. And if that turns out to be true, that nicely demonstrates a potential niche area for MWA, and it kind of explains why those kind of pulsars were not discovered in the earlier searches, particularly the Parkes low frequency surveys. So we are trying to get some convergence on some of these points, and we will be publishing this discovery and highlighting MWA's potential in an upcoming paper. So a few weeks ago, then Nick sent me this email, and he thought he almost discovered a second pulsar. But unfortunately, that excitement was really short-lived because it was already claimed by Arecibo last year. So these are the kind of things that we have to get used to it. And so that basically pushes us to keep hunting and find more pulsars that are waiting for us to be discovered in the camp. So where do things stand now? This is a combination of the two pipelines, and we have nearly tripled the pulsar count from MWA. So compared to the publication from 2 years ago by Meng Yao, so we have nearly 3 times the pulsar at this point, with the important distinction that many of them we are now detecting with a much higher sensitivity, a larger subset of them in full polarimetry. So there are a couple of very nice projects that are centered around it. So Nick Swainstein will be focusing on pulsar population studies using this sample and for his PhD, and Keegan's master's research is focused on understanding the pulsar emission by looking at the frequency dependence of pulsar property. Okay, so the another nice thing about this MWA service is that we are recording voltages. So we can correlate them, image them, and use those interferometric advantages to aid our pulsar search efforts. And that is essentially the direction we are pushing Susmita's project. Susmita Seth is a Curtin's new PhD student working in this area. And here is an image that she has produced, and using Martin's pipeline that runs on a Magnus cluster. This Stokes I of a large field 16 by 16 degree, and this is Stokes V. And you can see those the black and the white dot, which is essentially the circularly polarized emission from 2 well-known pulsars. One of them is a Assamese pulsar that is shown on the left, and the other is a millisecond pulsar that is on the right. So, and she is one of the early adopters for porting and benchmarking this pipeline on the new Garavala cluster, if I say it right. Anyway, so there's a nice, interesting follow-up from her master's research that she did at University of Manchester, which is essentially looking at field containing one of her supernova targets. And here is an image, and as you can see, it's not the most impressive one, and you are only getting down to something like 100 millijansky. That is for the obvious reason, because unlike Glima and other imaging people, we have not been paying a good attention to keep things like signus A out of the beam. But even then, you can see this first pulsars, which is actually the first pulsars, one from Jocelyn Bell, and this is the first millisecond pulsar. In fact, it's the first detection of this millisecond pulsars with the MWA. But we have not been able to see this moderately bright one, and which is this red circle. And that is a challenge for Susmita, basically clean up this image and get to that sensitivity so that we can push this direction as an interesting alternative strategy for finding candidates in imaging and doing targeted searches. Meng Yao is leading a very interesting proposal that's going to use a combination of FAST and MWA to do some contemporaneous single pulse searches. So basically the idea is to coordinate the FAST observations with upcoming smart observations, and we can do some contemporaneous multi-frequency pulsar surveys specifically targeting the population of single pulse emitting pulsars, which are hard to discover and even harder to follow up. So essentially looking at the population of rats and intermittent pulsars and giant pulse emitters, the proposal is currently pending. And so if successful, then we will be trying to coordinate that with the MWA so that we can really take advantage of geographic locations and common sky coverage of these two very good instruments. Like I said, VCS is also beginning to be exploited for all range of other transient science, and you already heard a lot about this from Alex this morning, and this is that ticker localization plot from the cosmic ray detection work that is going on. And here is another application of VCS, in fact, non-astronomy applications using MWA as a passive radar. And you heard about from Paul this morning and Steve Prabhu's work, and this is something similar sort of a category, but in this case using a VCS and high time resolution VCS data to detect satellites and other space debris. So Brendan has a paper that is at the final stage of a collaboration and will be submitted very soon. Brendan is a PhD student working with Stephen Tingay. I can't resist to show this because I'm a pulsar person. So when you see the pulsar with 2% of MWA, it is something really tempting. And the EDA, as you heard from Martin this morning, is a sister telescope of MWA built out of MWA's technologies, primarily as like an SKA prototype machine. So at the moment, it can only record a 1 megahertz bandwidth, but that's like a 2% of MWA sensitivity. But it might play an important role because it's a good practice ground for like looking at the pulsar monitoring type projects that you can do with eventually with the MWA when we have like a phase 3 and the real-time beamforming capabilities. Okay, so normally at this point, I would say that what we are going to do in the next year or so, but it has been quite a crazy time all around the world. So I thought I will just go back and reflect a bit on what I actually said 6 months ago in a Tempe meeting. These are my slides from a Tempe meeting, and where I said, okay, one of our goals for the year is like building and establishing that pipeline, end-to-end pipeline going from data collection at MRO, doing all the array calibration and data quality checks at POSI, and the processing the data for pulsar searching on O-star. And that is pretty much becoming a routine. And as you have seen that we have basically looked at every single VCS observations for this purpose, at least until the second stage. The other important goal was to develop the software, benchmark them on O-star, and integrate them with machine learning software that we are currently adopting from the LOFAR team. And that is more or less in a good order. And the next pipeline is running on O-star with the next flow implementation that he has managed to do recently. It is another factor of 2 improved benchmarks. And we are now looking for like, a summer student to integrate the machine learning side of the project. We are doing a first pass shallow search, and you have already seen the first new pulsar, which is a light near the end of a long tunnel. And Susmita is on the task of image-based candidate finding techniques. And we are working with the ADAX team to integrate our the candidate database. And you have seen the pulsar tally from Keegan's project, and things are running well. And we are about to reinstate our monthly busy telethons. Pipeline is being benchmarked on the Shanghai machines, and we are also doing like a good job of integrating the new students. So those who are interested, that there is, we have a weekly meetings at Curtin, and we have a Pulsar wiki, and there is a Slack channel. So feel free to contact any one of us. And that is my summary, and I'm happy to take any questions.
Okay, thanks, Ramesh. Unfortunately, I don't think we have any time for questions. So I'll encourage anyone, if they have questions, to post them in the chat. So thanks again, Ramesh. I'll applaud on behalf of the participants. And now we're going to move to Sam. So Sam, do you mind sharing your screen, please?
Oh, yeah.
I think Ramesh has to stop sharing first.
Yep.
Thanks.
Okay, sharing my screen. Is that there?
Yep, looks good. So next we have Sam McSweeney, who's going to talk to us about an interesting pulsar. Thanks, Sam.
Thank you. I'll just point out, by the way, this is my bid for the best background. I couldn't figure out how to make a virtual background, so I've just decorated my my home office there. Thanks for letting me speak about this. Some of the work that I've been interested in for a long time, and also I've got a third-year student, Garbutt Grover, who's been working on some of this stuff as well. So a lot of the plots I'll show later in this talk have come from Garbutt, and it's ongoing work. So hopefully I'll be showing you some interesting open questions that perhaps anyone who has any ideas in the audience can offer some insight into. That would be amazing. So there's two parts to this talk, really. There's the high time resolution part. So I'll spend the first little bit talking about what I mean by high time resolution, which everybody seems to have their own version of what high time resolution means. And then I'll get into actually using that system to look at this very interesting pulsar and its polarization properties. So pulsar people, it depends what your science case is, what you need in terms of time resolution. Some of the big science goals of pulsar that have to do with pulsars are gravitational waves, dense matter physics, test of general relativity. All of those three either directly or indirectly require observations of millisecond pulsars at a pretty high time resolution in order to be able to resolve profiles of millisecond pulsars quite finely. Now, the science question that I'm most interested in is actually none of those. It's the first question that was asked when pulsars came along on the scene, which is why is it that they're giving off light in the radio at all? And what we don't understand yet is how the relativistic plasmas that make up their magnetospheres operate. So I'm interested in the emission physics, and obviously slow pulsars, slow rotating pulsars, by which I mean on the order of a second, versus millisecond pulsars that rotate on the order of milliseconds. Across the whole gamut, they all emit radio. So we have to understand a process that operates on a large range of timescales. But in particular, when you are interested in the emission physics, okay, so here on the bottom, I've got a log scale of time scales. And what I'm showing at the moment is just how it's a histogram of all the known pulsars, their rotation periods. So you can see the millisecond, I don't know if you can see my cursor, but here's the millisecond pulsars as the little left lump, and then the larger population of slow or normal garden variety pulsars on the right-hand side. But if you want to study the individual pulses of these things, which is a crucial aspect to studying their emission physics, then you really need to go a few order of magnitudes further down in time. And it's been known for a very, very long time, several decades, that you can actually probe even finer timescales and discover that they vary on microsecond timescales. And in a few niche cases, for example, the crab pulsar is the prototypical example, there's nanostructure, so variation on nanosecond timescales. And each of these, of course, also come with it. The reason why it's interesting for emission physics is because each of these timescales represents a different size scale that you're probing in the magnetosphere. So when you get right down to the bottom end, you're looking at things on meter timescales. So apparently the magnetospheres of pulsars are very dynamic, turbulent things, and we need to be able to probe them on these spatial scales to understand what's going on. So as I hinted on the previous slide, the vast majority of very popular pulsar science cases require timescales. Kind of, this is a very rough line here that I've drawn, but you need you need a system that's able to probe timescales down on the microsecond level or below. But the standard MWA VCS pipeline, which has been talked about already several times, after it goes through the channelization stages, what pops out at the other end is something that is where your time resolution is 10 to the -4, so 100 microseconds, which is up here. So you can do some pulsar science with it, but you can't necessarily get to what might be potentially some really interesting studies. So this is just a quick recap of what Alex already showed us, which is the VCS pipeline, and Ramesh showed us in different forms. So the waves come into the arrays on the tiles, and you get and the voltages are sampled at some rate. Then it goes through a first channelization stage via a polyphase filter bank, and you end up with something that's just under a microsecond time resolution, and then you get your 24 1.28 megahertz frequency channels. Then you go through a second channelization stage, the fine PFB, and you sacrifice more of your time resolution for increased frequency resolution. And it's at that point that that we see the data for the first time. So that's when it's saved to disk. And I've been told on high authority that this little graphic pretty accurately reflects how people feel about the size of the MWA archive. But certainly when we're talking about petabytes, that's how it feels sometimes. Once we've got the raw voltage, the voltages, the complex voltages saved to disk, then we can do our beam forming and our other post-processing to actually detect the pulsars. So that, once again, that through this normal chain, what comes out of the fine PFB is at this time resolution. But if you looked at the numbers on the previous slide, then what we could get out, if we could access the pre-fine PFB time resolution, then we would be sitting down here. So we could do a lot more potentially. So here is just that section of that pipeline. And here what we want to do is to introduce a synthesis polyphase filter bank, a synthesis filter, I should say, to recover those original voltages. And what Alex alluded to was that you have to choose a filter of some sort, and there are various conditions that have to be met to be able to do that perfectly. We are not in that situation, so we can at best produce something that approximates the original. But that approximation equates to roughly less than, or on average, 0.5 dB signal loss. So that's pretty minor, and something we can certainly live with. All of this has just been accepted for publication in PASA, and there's an archive link there if you're interested to read the details. So people who are familiar with pulsar signals may recall, Ramesh alluded to this as well, that pulsar signals and any temporal signals are dispersed by the interstellar medium. And what that means for any people who are not sure what that means, it means that if you've got some fixed bandwidth that you're stuck with, then when you go to line up the pulsar again by artificially delaying each frequency channel to line up the signal, the best you can do is limited by the amount of dispersion that's going on, which is characterized by the pulsar's so-called dispersion measure, and your frequency resolution. So if you had a smaller frequency, a higher frequency resolution, if your frequency band is smaller, then this problem is mitigated and you can actually resolve finer structure. Now, so this sounds like a bad thing to go back to a data product which has larger channels, because you'd suffer this effect more. But what we've introduced into the new pipeline is the fact that we are also recording the complex voltages, which means that all the spectral information is still there. And later on in post-processing or later down the pipeline, at any point with those voltages, you can still do effectively the equivalent of using the phase information to de-disperse as if you had perfect, as if you had extremely fine channels. So that process is called coherent de-dispersion, and it's an important feature of our new developed pipeline that's been active since about last year. To show what kind of difference that makes, I've got a few examples. Here is a pulsar, a millisecond pulsar that has been detected with the old pipeline. So this is with the 100 microsecond resolution, and the amount of the restriction of the time resolution that you can detect is given by this so-called DM smear, and you can see on the plot there's some arrows indicating how much that represents in time. But when we reprocess the same observation with the new pipeline, then you can see this much finer structure, and you can see also for the first time was discovered these precursor components. And this pulsar in particular has been studied in detail by Dilpreet, who's talking after me, I think. And here is a link to her paper that she published last year on that. Another very popular pulsar for timing studies and other studies that this is what I think of as Ramesh's favorite pulsar. So you can see the DM smear is a lot smaller here on account of this pulsar having a much lower DM. But still, when you reprocess it with the new pipeline, you can see what pops out is some finer structure, some little notches in the profile that weren't visible previously. And finally, this example here shows a special observation we made with the new system of a very bright pulsar. This is one that Ramesh also showed on his slides. This is actually a single pulse viewed across our 30 megahertz bandwidth. It's extremely bright, and you can see in this single pulse that it's very, the red is showing the linear polarization and the blue is showing the circular polarization. And so it's an incredibly bright pulsar and an incredibly bright pulse. Now I'm showing here a time resolution of around 200 microseconds, but using the system, of course, we can drill this down even further. So here is the same pulse zoomed in to 50 microseconds and then zoomed in again to 4.7 microseconds. And I just want to point out that the what looks like noise in the structure of that pulse is not noise. It's actual structure of the pulsar. This pulsar is already known to have a microsecond resolution, but no one has actually previously studied this in full polarization. So so we have this data set. We have other data sets, a lot of data sets just awaiting to be discovered, where we can study the microsecond structure of pulsars in full polarization at low frequency. So this is a new parameter space that we're excited to look into. This is what Ramesh called my pulsar. This is the one that I studied during my PhD. And so I wanted to use our new hammer and on this particular nail. So this is a single pulse again from this pulsar. And this pulsar has been known to exhibit some very bright, narrow events, narrow in time, Some people have called them giant pulses, but that's probably a bit of a misnomer. However, so I wanted to see whether or not it showed anything. So this is the data set I handed to Garvit, and he went through and was looking for microstructure. Here's an example of a pulse with a very sharp, narrow feature in it. And actually, I'm not showing it here. The time resolution I'm showing here is about 50 microseconds, but I have verified that this pulse is probably closer to about 10 microseconds wide. And the great thing is because it's so bright, you can look at it across the whole band. You should see in the lower panel, if you count them, those are the 24 coarse channels available to us. Here's another example from the same pulsar. And this time I've shown the frequency on the y-axis and time on the x-axis like before on the right-hand plot. But here are the different Stokes parameters, I, Q, U, and V. The Q has a question mark because I have reasons to doubt whether it's actually Q that it's showing, but that's a different topic. But what we noticed down here in the Stokes V was that there was this strange flipping of the circular of the handedness of the circular polarization as a function of frequency. So these dark patches versus these light patches, that's where it's apparently flipping from left-handed circular polarization to right-handed circular polarization. And I certainly wasn't expecting to see anything like that. Here's the previous pulse that I showed you, and here is the circular polarization on the bottom panel. And you can also see this very interesting Stokes V structure. This time on the left, it's more negative than on the right. And you still have this kind of banded structure going up in frequency. So this completely distracted us from looking at microstructure, and we wanted to look at the polarization a bit more. Here is what an average pulse looks like for the same data set. Now you'll notice that you can see many more than just the 24 coarse channels, and that's because we have the luxury of going back and reprocessing the same data set using the traditional pipeline that gives us the 100 microseconds, but it gives us the 10 kilohertz channels. So here is us having reprocessed that data, and on average, you can see that there is still this banded structure in Stokes V. So this is giving us a little bit of, well, the question is it real? So there are really three main possibilities. It could be intrinsic to the pulsar, this Stokes V property. It could be some kind of propagation effect, or it could be an instrumental effect. So we had to think of ways that we could verify whether it's intrinsic or not. And again, we can rely on the beauty of the fact that we can go back and reprocess things. And so here, what I'm showing is that reprocessed in giving us the highest time resolution mode. And this is a Stokes I. Each column is basically a single pulse. You can see gaps, vertical gaps. That's where the pulses actually turn off. So this pulsar is one of those that nulls, which is to say that simply that the pulses turn off from time to time. And but you can see the structure, horizontal structure. And that horizontal structure is the scintillation due to the ISM. So the bandwidth, the scintillation bandwidth doesn't at all match up with the larger, the frequency, the characteristic frequency scale of the Stokes V property. So on that basis, I'm ruling that out. I see I'm out of time, so I'm going to have to hurry up. We did go to other pulsars in the same field. So this time beam forming on a different pulsar, but using the same data set to see whether or not we could see the same feature in those. Obviously, if we could, that would cast doubt whether it's a real thing. But the examples we showed didn't have very bright circular polarization, so it's a bit inconclusive. But I've ruled it out nominally on the basis of the other evidence, which is that this pulsar, like many others, has different orthogonal polarization modes. And if you close one eye and squint with the other, you can make yourself believe that on average, there seems to be negative polarization on the left-hand side or the leading edge of the pulse, and it's positive on the other side. And this lines up with the different orthogonal polarizations and when one of them is dominant versus the other. So on this basis, I'm happy to expect that there is probably a real thing and a real intrinsic property of this pulsar. How do you get such a flipping of Stokes V as a function of frequency? Very quickly, so the orthogonal polarization modes, you can get it if they're mixing in some way, in some coherent way. If the phase relationship between the two orthogonal polarization modes is related. So one little toy model is that, for example, if the place where the one orthogonal polarization mode is generated is a fixed distance away from the place where the other mode is generated, then as a function of frequency, there's a different number of wavelengths that occurs between those two positions. And the result is that when they interfere with each other further down the track, you get the circular polarization flipping sign regularly as a function of frequency. It doesn't have to be the two the emission sites don't have to be distinct. It could also be evidence of a birefringence in the magnetosphere. So to sum up real quick, we have this new mode that is now available, and we as a group are very happy to help people make use of that data, of that pipeline. We're starting to look at some really interesting properties that of different pulsars that previously were unable to be investigated in this way. And we think we've seen possibly for the first time this really interesting structure in Stokes V that we have yet to investigate further and have yet to, and we've got to model better and see if we can understand what it's telling us about the magnetospheres. And that will do. Thank you very much.
That's great. Thanks very much, Sam. In the interest of time, I'm going to recommend that, again, questions be posted in the chat for you to answer. Zhang's already posted one, which was also the same as my question. So if you could just answer it in the chat, that would be great.
Will do, will do.
Great. I'll also applaud on behalf of all the participants. Thanks very much again, Sam. So next up we have Dilpreet. So Dilpreet, do you mind sharing your screen, please?
Give me a second.
Can you move a bit closer to the mic? You're quite quiet.
Yes, so can you all see my presentation?
Yeah, that looks good. If you could just start presenting mode, then it will be full screen.
So I'm turning it to the full screen.
That's
so
great.
Is it all visible?
Yeah. So Dilpreet is going to tell us about DMs towards MSPs.
Thanks, Charlotte. Hi, everyone. So I'm Dilpreet. I'm a final year PhD student at ICRAR Curtin. And today I will be talking about something which kept me really busy from the last several months. So I will be talking about dispersion measure towards a very important millisecond pulsar, which is 10^-41 5^36. And thanks to Sami and Ramesh for building up the base for my talk. So how can I change the slides? It's not changing.
Sometimes I have to push. Oh, there we go. It looks good.
Thanks. Got it. So as you all heard from Sami just now, that there's a recent development in the pulsar processing pipeline with the MWA, and which is PFB inversion, and that turned out really really great for the MSP, short period MSP studies with the MWA, where the 100 microsecond 10 kilohertz original native resolutions of VCS were not enough to distinguish the temporal features in the pulse profiles and to phase coherently disperse the profiles. But thanks to this development and thanks to Sami, and with this we are able to detect the pulsars down to 80 megahertz, and we were getting a very good timing precision of the order of 1 microsecond. So this is my favorite pulsar, 2241, as Sami also mentioned. So these are the detections with older and the newer processing pipelines. So the gray ones are with the 100 microsecond 10 kilohertz resolution, and the colored one are with the new beamforming pipeline, which is PFB inversion. And Sammy also showed, so I will not waste much time on this, that this one is with the 100 microsecond resolution, and with the new development we saw the pulse profile turned out very narrow, and we saw two cute looking precursor components as well, which were earlier buried somewhere inside the pulse profile because we were not able to coherently disperse our data. So the very interesting frequency coverage of the MWA from like 80 megahertz to 300 megahertz is really suitable for the interstellar medium studies towards the pulsars and the line of sight of pulsars. And so here I'll quickly like to mention the two different modes of observation with the MWA. One is, we all know we have 30 megahertz bandwidth, which can be used as a continuous mode, anywhere between 80 megahertz to 300 megahertz, or it can be split into different frequency channels, spreading through anywhere from 80 megahertz to 300 megahertz, which is also known as the picket fence mode of observation with the MWA. And I'm using this picket fence mode for my pulsar observations. And because this helps me to cover the larger frequency range from 80 megahertz to 300 megahertz, that helped me a lot to with this and along with the VCS development, along with the PFD development, I was able to measure the dispersion measure with very high precision of the order of 10 to the power minus 6 parsec per centimeter cube. So again, when we found that very nice looking precursor components in the pulse profile, we quickly compared our data with the PARCS, because this is a PTA target, and PARCS telescope is continuously observing this under the timing array experiment. So, and we saw that these precursor components only appeared at low frequencies and very faint or almost negligible at the higher timing frequencies. And all this data, all these results are published in my publication Correlator. So if you want to look at how we did the GM measurements and the spectral studies of this pulsar, you can go and check out my paper. So the major thing was there was a huge gap between the MWA and PARCS frequencies, and we found that the GMRT is the only ideal instrument on the telescope which can cover, which can fill in this frequency gap. So this was an important target, and we were motivated enough to proceed further with this target. So a few points about this, what motivated us for the work. So the first one is it's a very important PTA target, and it is in a 3.5-hour binary orbit with a black widow type companion. So the eccentricity of this binary system is very low, and the companion is not eclipsing the pulsars, so which is a good thing. But there are many recent studies which shows that for some of the binary pulsars, there are DM contribution or DM modulation coming from the companion winds. So as we can reach very good precision for this pulsar, good DM precision for this pulsar, so we were highly motivated to look at the full orbit of this target and to see what kind of orbital DM dependence we can see for this particular target. So the another thing is this pulsar has very narrow profile width and almost negligible profile evolution for the main component except the precursor components. So it's really important to understand how the precursor components also evolved, and to look at the missing frequencies between the MWA and PARCS. And this is again really important because this is the era of wideband timing, and profile evolution could impact the noise budget of the PTA pulsars. And another important thing is to understand the frequency dependent dispersion measure, which is also known as chromatic dispersion measure. So this was theorized by Cordes et al. In 2016, but till now there is no direct evidence of chromaticity towards any of the PTA targets. So I will be talking about this chromatic DM later in my slides. So coming to the full orbit data, so all these points were enough to motivate us for the work. So we started with the orbital to see the orbital dependence of the DM. So the full orbit is 3.5 hour, but the VCS constrains to only 90-minute observation. So this was a real challenge. So we made a different proposal and performed a very special observation for to cover the full orbit of this target. So what we did, we took 10-minute snapshots and 10-minute gaps and 10-minute snapshots to cover the full 3.5-hour orbit within the 90-minute limit. So we usually observe this pulsar for like 1 hour to 70 to 80 minutes for usual DM and other analysis, but we have reduced the time to 10 minutes, so which means we have reduced the sensitivity. So we compensated that with increasing the subband frequencies. So instead of using the typical 1.28 megahertz frequency channels, frequency sub-channels, which were spread through 80 to 300 megahertz for this pulsar, I chose a very different frequency setup for this special observation. So after getting the proposal accepted, we got 8 observations, which were covering full 3.5-hour orbit, but there was another challenge. So this observation came up with no calibration observation. So we don't want to throw out this very important data, and I came up with a new technique, which for which I carefully chose another calibration observations, which were taken at different frequencies with different frequency setups. So, but very near to my pulsar observation. So I downloaded all of them, I calibrated all of them, and then very carefully chose the frequencies which were required for my pulsar observations, and then calibrated my 3.5-hour full orbit data for this pulsar. So this was a real challenge, and we did it for the first time, and yeah, we succeeded. So after getting the full orbit data, I ran through the DM measurements, and luckily we got very high precision this time again with 10⁻⁶ parsec per centimeter cube. But before showing the full orbit DM measurements for this pulsar, I would like to mention very important effect which confused us a lot when we looked at our very initial data, which came out of the pulsar processing, initial processing softwares. So if we look at the PS archive data, so this was, so there was a confusion. So basically for the, which is known as apparent chromatic orbital effects in pulsars, or ACOE, so which is basically a combination of few different effects. And one of them is most of the pulsar processing softwares are not computing the dispersive delays using the barycentric frequencies, which can induce an apparent annual variation of DM with the orbital phase. But luckily, what this plot is showing is a simulated data. So there's a quote from Andrew Cameron, from who is actively working on such effects. So we simulated for 20 to 41, and for 20 to 41, and this was what the PS archive or other softwares will not be taking into account. But luckily, our timing softwares are taking into account properly, and this is how my DM measurements were done. So what you see here is, I can choose the orbital phase instead of MGD. So these are the full orbit measurements of 20 to 41, so covering the full phase. And so here is the delta DM, and here x-axis is orbital phase. So now we didn't saw any ACOE effect in our data. So what we saw is something which is completely coming from the binary system. So now the companion winds can also contribute, but the variations in DM are too small. So we can rule out the fact that for this particular pulsar, the companion winds are not contributing much to the DM measurements. So the orbital dependence of DM is ruled out for this particular target. So the next thing is the chromatic dispersion measure, which is also known as frequency dependent DM, and it arises from the multipath propagation caused by the scattering disk, which is somewhere in between the pulsar and the observer. So this is a cartoon from Cordes et al. And so this scattering is, so the observing frequencies are highly sensitive to the area of the scattering disk. And this sensitivity is highly dependent on frequencies. So it goes as frequency to the power -2. So which means that at lower frequencies, so which means that the volume we saw or we sample, volume of the scattering disk we sample at low frequencies is much larger than what we sample at higher frequencies. So which means that the rays coming are traveling the longer paths, and there are chances that they have traveled to a different medium. And thus there's a tendency that they can produce different DMs at different frequencies. But again, this is the theoretical effect which Cordes et al. Mentioned in 2016. And till now, there is no direct evidence of chromaticity for any of the PTA target over the larger frequencies. And this is also a very subtle effect and cannot be measured very easily or straight away. But now with the MWA, we can reach to very high precision in DM. So we can surely try to look at for such effects. So for that, we planned an observing campaign with 3 different telescopes, MWA, PARCS, and GMRT. So this happened in November last year. So the MWA was covering 80 to 220 megahertz frequency range. The GMRT, we chose band 3 and band 4, which were 350 to 550 and 550 to 750 megahertz. And then PARCS, there was a new receiver, ultra wideband receiver, which covered from 700 megahertz to 4 gigahertz. So there were many challenges in getting this data done. The first of all was getting the proposals accepted for this campaign, and luckily we went through that. And then for the GMRT, it can easily observe like -54, -55 in declination, but the pulsar is -52. So the pulsar was visible to GMRT for only for few hours. So which developed a further constraint to co-observe with the MWA and PARCS. But thanks to Ramesh, Andrew, and all the other people who helped me in the observation, we managed to take observations contemporaneously at 3 different epochs, which I will be showing. But before proceeding further, I would also like to mention that there were also many challenges in dealing with the data from 3 different telescopes. So MWA data has its own complex calibration. The GMRT, for the GMRT data, it was very confusing, and it turned out half a channel frequency offset in the data. So we turned out downloading and processing all the GMRT data again to service this problem. It took us some while. And for the PARCS data, so because it's a huge bandwidth and you will never get RFI clean data, so I learned and used a very specialized software which is known as Coast Guard. It's developed by Shodai, my CAS supervisor. So I learned and ran through the PARCS UWL data through Coast Guard to make my data RFI cleaned. And there was still some RFI which I manually removed, and then we were all set to go with the data from all 3 different telescopes. So the first thing which I did is to fill in the gap between the PARCS and the MWA. So here are the 2 profiles from GMRT from band 3 and band 4. So you can clearly see the component is visible at the lower band of the GMRT, but how these components has fully evolved, the more detailed analysis, the phase analysis of profile is required, which I'll be doing in further. So, so from looking at this pulsar has showed very less profile evolution as compared to the other PTA targets, for example, 0437 or 2145, where you can see the 2 components completely shooting at different frequencies up and down. So for this pulsar, we can say that there is almost negligible profile evolution. So because my observations were planned and done in a very specific manner, and so we managed to get observations at 3 different epochs. So and we carefully chose the 24-hour block to rule out the temporal variations in DM, which can happen from like one day to another, or not one day to another, but within few days to few months or years. So we took the data at 3 different epochs. So from at 12th and 13th of November, we were unfortunately having no MWA observations, but we got band 3 and parks. And because these are within 24-hour block, and assuming that the ISM has not changed significantly within the 24-hour, we can say that the temporal variations in DM for this particular pulsar and in these particular observations are ruled out. And as I earlier showed, the orbital DM variations are also ruled out because we didn't saw much variations in DM over the full orbit of this pulsar. So what's here is the DM from all 3 different telescopes. So the x-axis represents the frequencies in logarithmic scale. The y-axis is the measured DM, and the x bars represents the frequency leverage. So you can see from here the MWA has ruled out from 80 megahertz to 220 megahertz, and this is GMRT band 3. And the Parkes observations were from 700 megahertz to 4 gigahertz. So we divided the Parkes observations into 3 different sets. And then we measured the DM at 3 different subbands to see the trend of the DM. So it's the Parkes band, Parkes UWL band was divided based on these 3 different frequencies. So another important thing which I really need to emphasize in this plot is the Y error bars on the DM measurements. So you can clearly see for the MWA, these error bars are really small. So we can measure very precisely the DM with the MWA. And so these measurements were 10 to the power minus 6 parsec per centimeter cube. And for GMRT, although these are not very clear from this type of plot, I should make a zoomed in version of these 2 plots. So the GMRT was reaching 10 to the power minus 5, and the Parkes observations were ranging from 10 to the power 4 to 10 to the power minus 3 parsec per centimeter cube. So that's why there are larger error bars on the Parkes measurements. But the important thing is that when we plotted all the DM measurements from like all 3 different telescopes, we clearly saw a trend in DM, which is clearly presenting the chromaticity in the DM over the large frequencies. So we can say that this is the direct evidence, first ever evidence of the chromatic DM towards this particular target. And same we saw for the another observing epoch. Again, the data was within 24-hour block. So we don't have the MWA observations for this 12th and 13th of November, but band 3 and 3 points from the Parkes. And again, on the next epoch, 29th and 30th of November, we saw MWA band 4. So band 4 GMRT was overlapping with the some of the portion was overlapping with the lower band of the UWL. So yes, and there were 2 observations from Parkes. One was on 29th, another was on 30th. So you can see those were also very clearly overlapping with each other. And again, another evidence that we are ruling out the temporal variations. So, and even if there are temporal variations, those are very small compared to what we saw from lower end to the higher end. So again, sorry, the time is up, but I will be concluding soon. So another thing was we did a fit, and so we fitted for a power law, and it was nicely followed by all 3 different epochs, very nicely. And my best fit, my power law gave me the best fitted DM, which is 11.41132, and the catalog value for this pulsar is 11.41151. But again, the precision is very high, and our data followed the power law in all 3 different epochs. So again, for the PT experiments, they are looking for the direct detection of low frequency gravitational waves, and they really need to reach out the sensitivity to 100 to 200 nanoseconds. But the kind of variations, the DM errors in the Parkes in the Parkes manner, we can say that at the timing frequencies, these large uncertainties in DM can potentially cause few microseconds of delay, which can be contributed to the PTA noise budget, and which is much larger than 100 to 200 nanoseconds of sensitivity, which is required for the direct detection of gravitational waves. So in the end, I would just like to conclude that if we proceed with such kind of observations, and we saw the similar looking trends which follows from MWA to the Parkes observations, then the MWA DM measurements can be used to model or to apply better corrections to the PTA data. And this is something should be a long running process. I will be finishing this year, but this is something really important which MWA can contribute and can perform. So I will be leaving with my summary slides, and all questions are welcome. Thank you.
Okay, thanks, Dilpreet. Again, we're over time, so now I'm going to encourage people to post questions in the chat window, and if you could reply in the chat, that would be great. So again, I'll applaud on behalf of all the participants. Thanks so much again, Dilpreet. Next, we have a talk from Zhongli. So Zhongli, do you mind sharing your screen now, please? Zhongli, I can't hear you at the minute if you're speaking. We can see your slides okay, but we can't hear anything at the minute. Zhongli, we still can't hear you at the minute, or at least I can't. Zhongli, perhaps you can try disconnecting and reconnecting and checking the settings of your audio connection. Okay, I think we're just waiting a couple of minutes for Zhongli to reconnect.
Stop. How about now? I changed the computer.
Ah, yes, we can hear you fine now. That's much better.
What is the, maybe it's the internet connection, because I was using Wi-Fi and now I'm using the wire.
Oh, possibly, yeah.
Yeah, and sorry to share screen. Can you see my screen?
No, can you share your screen again, please?
Screen.
Oh, yeah, there we go. We can see it now.
Slideshow play from start. Okay, so
great.
So
Thanks very much.
fine, right? Yeah, I'm so sorry for this bug, but I will finish my talk quickly. Yes, thanks to the chair that to give me this opportunity. I'm going to talk about, so this is my title, MWA VCS pulsar search. This is mainly with incoherent beam and the beam forming on CSCAP. And this is the authors, and we are supported by engineers in Shao, and also we have collaborators from Curtin, Nick Swanston, and Mengyao Xue. And Mengyao is now in FAST, as Ramesh has already said. Okay, and this is my content. Firstly, I will talk a little bit more detail of the China SKA Regional Center prototype. And then I will briefly talk about our test of the MWA VCS incoherent pulsar search. And then we will discuss about the ability of the VCS side lobes, and then in the end, I wanted to talk about the beam forming, but because it is just recently updated, so I cannot talk with this one now. Okay, and then for the China SK Regional Center prototype, that we start its construction in 2018. And now from early of this year, it is in commissioning, and you can find its introduction in this paper. And that this computing set, we put it in the Shoshan campus of Shanghai Observatory, and in the map, you can see it is here. So it is a bit far from the city center, but we have a very large place for it. Okay, and this is the setting of our machine, that it has a total computing ability of around 200 T-flops, and it is constructed as the following, that we have 8 Intel x86 nodes, and we have some in Intel KNL nodes, Intel KNM nodes, and we also have some Huawei ARM nodes. So for the CPU, we totally have around 1,700 nodes. 1,700 core. And for the GPU, we have 16 nodes in total with the NVIDIA V100 chips, and the GPU total computing power is above 100 T-flops. And for our storage, we mainly use Huawei Ocean Store 9,000 and plus some disks. So in the end, we have more than 4 terabytes. And what to mention is we have some SSD. Now it is 138 terabytes, but we're going to update it very soon to be a bit more. And also in the next few months of this year, we also will triple our CPU nodes with the Intel x86. Okay, and for the data transfer, now we can transfer from Perth to Shanghai. There are some routes. There are some 2 different routes, but I won't mention now. And the wire is in total is 10 gigabits. And if you need to use this line, you have to tell our engineer, and then it can reach above 3.5 Gbps. And we will also test soon the connection from Spain to Shanghai, and this is also a 10 Gbps wire, and we have expectation to reach around 7 to 8 Gbps. Okay, and for what we have on our CSCAP now, that we have all optimization of the Gleam workflow on the ARM platform, and we have our AI applications of radio galaxy classification, source finding, pulsar identification from diagnosed plots, and we can do imaging of MWA 21 CMA, LWA, and VOA observations, and we have some ASCAP Dingo pilot survey data, and as Dr. Shui has mentioned that we have our transient pipeline based on the GPU, and then we also have some MWA VCS parser projects. Okay, so this is our test of the VCS incoherent parser search. We use 50 VCS incoherent summed data, and that the observation time is ranging from around 10 to 80 minutes. And this is very shallow, but this is a whole sky survey, almost a whole sky survey, that it covers around 30,000 square degree of south sky with this gain value. And you can see this sensitivity map, that we have a total coverage of the whole sky around 80% and above 50 milliyansky of the flux at 185 megahertz. The coverage is around 40%. And if you want to reach 10 milliyansky, then the coverage is only about 10%. Okay, and our searching steps is normal. We just follow the general steps with Presto, that we first remove RFI and then the dispersion and blah, blah. But what is different for our process is at the dispersion step, we have two working flows. And one is we use the DD plan for the low frequency by Nick, and you can see the table here. And this means that with the different DM value, when you do the dispersion, you have a different steps, and then you will have a different time resolution for it. And this table is a bit more detailed than Presto, but they're basically very similar. And then again, that we try another working flow, that we use a higher constant downsample for all the DM range, that we choose 2, 4, 8, or 16. That we fix this value for the whole DM and to see what is the outcome. And then for these two working flows, we have a different Zmax value, means whether we consider it as in the binary system or not. And for the working flow B, with the constant downsample, that we choose Zmax is 0 in order to save time, because it will be more time consuming if you choose Zmax is 200. And because we expect that we search only the known parsers, so we sift the candidate and we don't fold the whole candidate. We just search from the list and to see whether we have find those known parsers from it. And with this working flow, and our computing time is around 150 to 300 core hour for 1 hour VCS data. Okay, and then you can see that this is our searching result. We have found 58 pulsars with the flux more than 20 milliyansky. And then what to mention is, I didn't mark with the points here, but you can see with the normal DD plan, the normal Presto working flow, we searched 26. And then if we use a abnormal higher downsample, then we search another 32. So which means that this is very strange, but this is true for the incoherent data, that with lower time resolution, you can find even more pulsars. Okay, and then we have some discussions. Firstly, we want to discuss about this downsample factor, that whether it has a choice based on some parameters. And here we define a sensitivity or a signal to noise ratio to be our predicted flux of every pulsar divided by the 10 sigma sensitivity of our observations. And you can see that this is the number of, so this is the number of pulsars versus its period and its DM or its sensitivity or its signal to noise ratio. And this red data means we use a higher downsample. And you can see the distribution is rather homogeneous, means that a higher downsample is needed in general in all the cases, despite of sensitivity or period or DM. But if you look closely, it is possible that a large DM or for a low sensitivity pulsars, they may prefer a higher downsample value. And this is easy to understand because these data are assumed to be more contaminated by the noise. Okay, and then we need to have a solution for this, because when you work with a lot of beams with the coherent data, you don't want to do the working flows twice or 3 times or 4 times. So we do wish this is only the situation for the noisy data, and when you increase the sensitivity with the beams, like beam forming, then this will not happen anymore. Or another way is you can increase the candidate number, but this is also not preferred during a real search. Okay, and our another discussion is we compare with the detected pulsars by MWA with Meng Yao's result, that Meng Yao did a research with 26 observations of our searching sample, and she has detected 50 pulsars from it with incoherent data. This detection means you use the period and the DM of the known pulsars and you fold the data. So you will get the folding pulse shape of every known pulsar, and you see which of them are significant. So this is a very guaranteed procedure, but to search is like a black box that you don't know any parameter and you see what you can get. And in the end, that we have found 42 from this 50, which means even there are some pulsars at some frequency that you can see them, but in the blind search, you can't find them. And this ratio is around, it's more than 80%. And we consider this is already quite good. And this is maybe the maximum that we can go for it. And you can see that basically, this signal to noise ratio 0 means its expected flux is above its sensitivity. And you can see that only this very faint point, these blue ones are from Meng Yao's sample that we cannot find in the search. So with the poor SN pulsars maybe not counted in the Presto candidate, so you cannot find them from their candidate that the Presto give. Okay, and you can see that there's no preference of DM or P at all. And then the last thing is we going to compare with the result from Gleam that Murphy has trying to find the low frequency pulsar on Gleam in 2017. And she has detected 60 from Gleam continuum survey, which has a sensitivity from about 250 to about 50 milliyansky per beam in a very wide energy range. And the beam width is actually lower than the VCS. And then you can see that maybe it seems like the sensitivity of Gleam is lower than the VCS incoherent data. And we compare that these 60 detections from Gleam has 53 in our sample field, but it only has 30 overlaps with ours, and as you can see. So these red circles are what we have found, and these blue dots are what Gleam has found. And you will see that seems like even with 2-minute imaging data, that Gleam can find more faint sources here that you can see. Yeah. And another thing is the Gleam data, it can go a bit more higher DM value, and it can also find a bit more pulsars which has a confusing time property like millisecond pulsar or some variable sources, because for image it's not very strongly affected by the timing. Okay, so but you can also see here that with the VCS data, it can find some obviously very bright pulsars, but the Gleam cannot find them. So which means that some pulsars are not very significant in flux, but maybe very significant in their timing property, that it is very significantly periodic to find in the time data. And with this approach, we really think that the MWA VCS and Gleam, they are perfectly complementary. And also for SMART and Gleam X, it is the same because I have compared their sensitivity and they're also very similar. So I really think that we should detect pulsar or search pulsars both with the time data and also with the images. Okay, and then I will briefly talk about the ability of MWA side lobe. This is because we have found 2 north pulsars in the side lobe of MWA VCS. And this, I think Ramesh has already reported last time. And one source is only with 1% of the total, the peak zenith power of the beam. And another source takes only 5% of the zenith power. And these 2 are the very famous bright pulsars in the north. That for this one, you can see the pulse shape, it is not significant, not very significant. So we don't calculate its flux. But for another pulsar, it is rather more significant and stable. And we can calculate its flux here, that you can see that the flux calculated from the side lobe detection is very much consistent with other data from other surveys. So this means that to use the side lobe to research on some north pulsars are quite possible. And then we diagnose the ability of the MWA side lobe. Here I put a question mark because I'm not sure whether it is really side lobe or not, but it is about, because we normally think the MWA limit is the north 30 degree, but how about between the 30 and 63.3 degree, that it still have some sensitivities here. And then that if we do a theoretical estimation, so this line is the incoherent line, sensitivity line, and this line is the coherent sensitivity line. And you can see that even in the very north, above 30 degree, that MWA VCS can detect some north pulsars with DM less than 200. And we can at least detect 4 incoherently and around 30 with the beam, with a tight array. Okay, so in the end, it's my summary that the China SK Regional Center prototype is in commissioning 2020, and we open to everyone. So if you want to use it, you can ask us to open count for you. And it with a total computing power of around 200 T-flops and storage of 4.5 terabyte. And we have a shallow pulsar search with 50 VCS incoherent data and find 58 non-pulsars. A higher down sample, which means a lower time resolution, will significantly increase the search rate, at least for more noisy observations. And the time frequency and imaging data have different advantages to be a great complementation for the pulsar search. So with this reason that we really hope to join the GLIMX team for the pulsar science. And in the end, we think the MWA VCS can also detect some bright sources in the north 30 degree to 63.3 degree, and that it at least can look for these 30 known pulsars in the coherent beam. So thank you so much for listening. I have finished.
Thanks very much, Zhongli. I agree that it's interesting to look at pulsars both in the time domain and in imaging data. We have some time for a quick question or two if people want to post a question in the chat or raise their hand. Maybe I'll just ask a quick question in the meantime. So I was just wondering how many candidates are produced from your incoherent beam search and how you sort through those.
Okay, these candidates are default. If you want to change the number, you have to change Presto. Presto inside its program. And we choose around 100 candidates roughly, 100 or 200 or 50. Yeah, and we cannot do more because without folding the candidate, it's not the normal procedure. You should have fold all of them, and this takes even more time than search itself.
Okay, thanks. We have a quick question from Kath. Can you learn something about the MWA's beam response by observing its declinations above plus 30 degrees?
Sorry, I cannot see the chatting panel. Where is it?
Oh, I just repeated the question. Kath's question is, can you learn something about the MWA's response by observing its declinations above plus 30 degrees?
To learn the response. Okay, this is something we never consider. And depends on what you want to learn from it. But I don't think this will be the main focus, the main science, because you're going to see something that the LOFAR can easily see. But I just mean that if there's some very quick event happened, that you do be able to use the MWA to catch it, even it is above 30 degrees of the north. And this is what I want to emphasize on. Is it fine?
Yeah, that's great. Thanks, Xiangli. Natasha also has a comment that people can contact Luke if you would like to be added to the list of people interested in GleamX, if you're not already.
Yeah, I have the email that whether to join the GleamX, and I also replied. But after that, nothing's going on. And so I'm wondering whether it is because of the telecom that we have to join the telecom first.
I can answer that. So it was delayed because of the project meeting, and the board meeting was delayed. So that meant that we've only just decided what's going to happen next. And Adam explained that there will be a follow-up to that soon.
Okay.
Great, thanks for clarifying, Luke. Okay, I will thank Zhongli again on behalf of all the participants. Thanks very much for your talk. And thanks very much again to all of the speakers in the session. So now I'll hand back over to the MWA management for the wrap-up of the meeting.
Yep, thank you, Charlotte. Assume you can all see me. We're looking at somebody's slides, so maybe you want to stop sharing your screen, Zhongli. All right, so this is going to be a quick wrap up. As I think those of you who read the instructions for the meetings would know, we actually ran 2 competitions during this meeting. So I have the pleasure of announcing the winners for that. So the first competition that we ran was the best Zoom background. So we're going to have a runner-up and a winner. So the runner-up is going to be Sammy for his home decorated old school style background. And Sammy, as a runner-up, you will get to have one of these beautiful MWA keep cups. You see that there?
Awesome, thank you.
They're very cool. You can see Ricky to get one of those. But the winner with the spectacular galactic plane MWA background was Chinoa. And so Chinoa, congratulations. We will also give you a keep cup. And you will get a piece of beautiful MWA merchandise in the form of a t-shirt. Again, Ricky can hook you up with that next week. The other competition that we ran was for the best talk. So in this particular case, we have 2 runners-up and a winner. So the first runner-up I'm going to mention is Jack Lyne for his talk yesterday, which has just put Monty Python in my brain. So congratulations.
Very kind.
Again, Jack, you can get a keep cup off Ricky. And the other one is Aman, who gave a very interesting talk on MWA beams and measuring beams, which I think is an extraordinarily useful result. So we will post you an MWA keep cup. But the winner for the best talk, as voted by Luke and Mia and I, the management team, was Ben Quichi for his talk on remnant radio galaxies. So I don't think Ben's online, but he's normally in the building, so we will provide him with his keep cup and his beautiful MWA t-shirt. So congratulations, and thank you to everyone who participated in the competition or not and presented at the meeting these last 2 days. So yay. It's weird with no clapping on Zoom, I have to say. Yay! So we're going to clap in the room. Yeah, cool. And I'm going to say what I said to Chinoa on Twitter last night, which is that in the low-res version, it looks like she's got fire coming out of her ears. Like, she's super angry. But in the high-res version, it's awesome. So, all right, I just want to thank everybody for their participation in the meeting, whether it be giving talks or engaging in the presentation discussions. And we will endeavour to, as I said this morning, run a process next week to get feedback on the phase 3 options. So I will send an email out to the collaboration on how you can participate in that. It will be a structured feedback process, so I don't want just random emails lobbing in, but we'll have a dedicated way for people to provide their commentary. We'll provide them with the documents to look at. I've already noted Divya and others wanting to be part of that process. So in addition to that, we will send out a survey next week about the actual format of the meeting and to get feedback on how you think this meeting went and how we could improve it for next time. Now, if you participate in the survey, we're also going to give away some merch. And in fact, one lucky survey participant, to give you some incentive, will not only get a keep cut and a t-shirt, but you can also have one of these beautiful MWA team jackets, soft shell jackets. So look out for the questionnaire, which Ricky will send out next week. All right. I think the last thing that I have to do in the wrap up is thank the people that made this possible. So in particular, Mia and Ricky and Luke, who did all the effort of putting all this up on Indico and communicating with people. And again, it's like 3 o'clock in the morning for Luke, and Luke has stayed awake this whole time, making sure that things are running in the background. So this, I think, is an effort above and beyond. So thank you all, and we're all going to clap here. Yay. And thank you all for participating, because I think this has gone extremely well. And despite the fact that we are not all in the same place as we would normally be, I feel that the sense of community and collaboration in the MWA is extremely strong, and it's a great joy to direct a project like this. So thank you all, and see you soon. I think that's it for me. Yay! See ya!
Thank you, Melanie.